Welcome to APEC. It's December 20th, 2025, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody watching this on YouTube and our other live stream channels. Again, we are multicasting this thing, and it is amazing. So today, Dr. Nathan Inan will present on Quantum Linearized General Relativity and its applications to propulsion. Orestis Lazanakis will be discussing the results of isotope tests conducted on purported ET material samples. Jennifer Nielsen will present on part 2 of her topological torsion warp drive bubble magnetohydrodynamic fluid and field coherence applications of TUFT. And Curtis Horn is going to be unveiling his long anticipated unified field theory. We're also going to have updates from our lab partners. We're going to finish off the event with open discussion by conference attendees. Drew is already in the studio. Nathan is already with us. He's raring to go. Joel Michalowicz, he is in the studio as well. We have more people coming in. I am super excited. So today's event is on StreamYard, broadcasting primarily through the Alt Propulsion YouTube channel. If you haven't subscribed, please subscribe to that now. You can ask questions using the live chat feature on the right-hand side of the screen. We will try to ask them to presenters, although they do scroll up the page pretty fast sometimes. You can also always view conference replays, details, and speaker info on our website at altpropulsion.com. So I don't have any major announcements for today, but we are closing out the 2025 year for APEC. This has been our 5th year of doing the conference. I am so excited. I have been going back and doing AI-assisted stories, as well as creating breakout presentations on past materials. And it just blows me away at the amount of innovation that we have been able to showcase. We have had all of the top innovators in this area present at APEC, often several times. And we just, I mean, personally, I feel honored and blessed to be able to help showcase what this community is doing and, do our small part to help move things forward. So without any further ado, let's get started with our first speaker for today, Dr. Nathan Inan. Welcome, sir. Oops, and he just disappeared. I think he hit the wrong button, so it may take us just a sec to bring him back in. There he is.
Thank you, Tim.
Yep, absolutely. It looks, you know what? I think your screen share went down as well, so we may have to do that again.
Let me run my screen share. Tell me if you see it. I'll go to share.
There we go. Okay, yeah, it is coming up. Yep, and again, you're talking about a formalism of quantum electrodynamics used to construct a framework of canonical quantization for linearized general relativity. So that is a mouthful to say, but I will. You have the expertise. I will let you present it. And just, we were chatting before we launched this. I am jealous as heck. It is sunny, warm, and nice down where you're at, and I'm stuck in rain central right now. So
sorry about that. No, lock into the physics and try to not think too much about the theory weather.
Yeah. Nathan, let me hand things over to you, and thank you again, man. It's always a true honor to have you with us.
Absolutely. Thank you, Tim. I appreciate it so much. I'm super excited, actually, that I get to join the lineup for the very last APEC talk of the year, and I get to kick it off here. So I'll jump right on in. The title of the talk there, Quantum Linearized GR with Applications to Propulsion. And as Tim mentioned, my name is Nathan, and I teach at Clovis Community College and Fresno State University. I'm also affiliated with UC Merced and with Texas Space in particular has supported this work tremendously. So I'll jump right on in and give you an outline of what I'll be talking about. So first off, I'll start with classical gravitational waves described by linearized general relativity, and lay down some frameworks such as the transverse traceless gravitational wave metric perturbation, define some electric-like and magnetic-like tensor fields, talk about the gravitational wave intensity, otherwise known as the Isaacson power flux formula, And then I'll go ahead and quantize the space-time metric perturbation. So that'll involve, as Tim mentioned in the title, canonical quantization of linearized general relativity in a way that's very analogous to quantum electrodynamics, or QED. I'll talk about some commutation relations that come out of that, the canonical uncertainty principle that we get, and the quantized Hamiltonian density. So that'll pretty much lay down the framework for where I'm going with this talk, in the sense of going from classical GR to quantized linear GR. I do show that you can also go the other direction. It's not trivial. I call it classicalizing the quantum space-time perturbation. And that's just to show that we do recover the correct Isaacson power flux formula from the quantized fields. And then I also demonstrate a connection with the Bohr Correspondence Principle, which bridges quantum and classical descriptions of electromagnetism, or in this case, linearized GR. So this right here, these 3 points are the basis of some papers that I'm working on with some students. And it's pretty much the bulk of what I'll be talking about. Now, Tim challenged me, happily, I accepted, to speculate a little bit and see what I can come up with in the area of propulsion. And I think I have some interesting stuff I can share. So this is kind of hot off the press, haven't written this up in a paper. Now, the papers we wrote do talk about quantum space-time foam, gravitationally bound neutrons, otherwise known as gravitational atoms, photon graviton gas models, and gravitational versions of the Stefan's law, Schwinger effect, and Casimir effect. Now, it's that Casimir effect right there. Tim brought up in an email that he takes an interest in it, and I very much do too. And it's a nice connecting point to propulsion, interestingly. So this last part here is indeed the speculative stuff. So this is the stuff I don't claim. I wouldn't hang my hat on this and officially say it has to be correct, but I think it's some interesting stuff to think about, which is whether quantum tunneling of the quantized gravitational wave field might play a role in propulsion. I connect that to the ER-EPR conjecture, basically connecting wormholes and quantum entanglement. We talk much about metric engineering, and so in the context of this talk, I talk about probability field engineering as sort of a alternative to metric engineering. And then possible alternative version of the warp drive concept, using this idea of quantum tunneling of the quantized gravitational wave field. All right, so let me, as I said, lay down some framework. Here's your Minkowski metrics, just showing you the signature I'll be using, which is -1 and then the rest +1. As many of us know, you can add a perturbation to the Minkowski flat space-time, and that perturbation represents gravity. And so it could be thought of as a gravitational field. And in fact, in an effective field theory, that's what allows us to quantize the field in a manner similar to how we would do it in QED. So visually speaking, you can picture it like you got flat space-time described by your eta mu nu, and then h mu nu allows for things to happen like stretching or compressing or whatever warping of space-time is of interest. So for the case of a gravitational wave, it's commonly shown that the transverse traceless perturbation is used. And we have two polarizations of gravitational waves, the plus polarization and the cross polarization. You can see them appear here. The plus is here on the dx squared and the dy squared, and the cross here on the mixed term. And so you could think of those very small, remember we're talking about linearized GR, very small perturbations. And so it's just kind of a rippling to space-time. Now this is a bit exaggerated in the sense that those kind of look like large amplitudes, I suppose you could say, relatively speaking. But we're in linearized GR, so they're very, very small. And as we well know, that's pretty much all that has ever been detected experimentally, say by LIGO, are very small ripples of space-time. That is very weak gravitational waves. So the transverse traceless perturbation has your plus and cross polarization terms in the center of the matrix, assuming you have a wave, gravitational wave propagating in the z direction. As you can see, it's transverse because the 3 divergence is 0, and it's traceless there, as you can see in terms of the Minkowski background metric, giving us the trace as 0. And it's commonly shown in a diagram that plus and cross polarization appear like this as far as like a single snapshot in time. If you want to imagine it more dynamically, like a gravitational wave coming at you, you'd have this stretching and squeezing of space-time. I'll mention, by the way, that although this is often referred to as the transverse traceless gauge, in other words, like a particular coordinate choice, it's been shown by Flanagan and Hughes back in 2005 that in linearized GR, this HIJ-TT, the transverse traceless spatial perturbation, is actually gauge invariant or coordinate invariant to linear order. So in other words, whatever we say about it, we shouldn't think that any effects could be just simply gauged away, or in other words, eliminated by a coordinate transformation. Because in linearized GR to linear order, you can show that this perturbation, the transverse traceless one, is in fact gauge invariant. All right. So with that mentioned, I'll describe a few other things that are commonly found in general relativity textbooks. That if you take the space-space component of the Einstein tensor, it turns out to be essentially a wave equation on the perturbation. In vacuum, then you basically have a homogeneous wave equation where I'm defining the box operator in terms of a flat space-time background. And so it's very analogous to electromagnetic waves. For those who are not quite as familiar with gravitational waves, I trust you would be familiar with electromagnetic waves. In vacuum, you've got your box operators acting on the electric and magnetic fields, giving you your propagating electromagnetic wave. So similar thing for gravity. Now, the interesting thing is that for gravity, you can actually define some tensors that act a lot like the electric and magnetic fields. So in other words, like the electric field being the negative time derivative of the vector potential and the magnetic field being the curl of the vector potential, there's a similar formulation that you can do in terms of tensors, where you can see the electric-like field is also a negative time derivative of the perturbation, and the magnetic-like tensor field is essentially also a curl. That's a Levi-Civita there, and a derivative acting on the perturbation. So those two fields, the electric and magnetic-like tensor fields, are very handy in this context because it allows us to work with analogies in electromagnetism very efficiently. So just to convince us that these are actual legitimate fields that produce motion to test particles, I wrote down here that just as we know the Lorentz force involves the electric field and the magnetic field, the geodesic equation of motion, which is sort of like the gravitational version of the Lorentz force, also involves the electric-like tensor and magnetic-like tensor. Now, you might notice, by the way, that both fields involve a velocity dependence there as far as the force that they produce. And we could talk more about that. And actually, I give a whole talk on that topic dedicated completely to this framework. So I won't digress too much that way. Now, what I will mention, though, is that you do get a gravito-Faraday law. At least I call it gravito because it's a gravitational version. It's essentially a curl of the electric-like tensor is equal to the negative time derivative of the magnetic-like tensor. And you can also show from the Einstein field equation, you get a gravito-Ampere law. Again, in vacuum, so you don't have the displacement current term, but it looks a lot like what you have in electromagnetism. And so just as electromagnetic waves propagate because of the mutual induction of electric and magnetic fields, so also gravitational waves propagate because of essentially a mutual induction of the electric-like and magnetic-like tensor fields. Now, this is where the math gets a bit nasty. Again, standard general relativity, you can find it pretty much in any standard general relativity textbook. The Landau-Lifshitz pseudotensor, in a sense, characterizes or describes the gravitational wave or gravitational field energy, energy density or flux. And if you're only interested in gravitational waves, it actually reduces very nicely to just what you see here for the Isaacson power flux formula. And that first expression there with the HIJ-TT, that's commonly found in textbooks. Now, because I'm using the electric-like tensor, this second way of expressing the intensity isn't commonly found, but it's super useful because you'll notice it looks a lot like what you have in electromagnetism. Like, for instance, if you have a sinusoidal field, and so you take the square of the time average, it just pulls out a factor of a half, basically, times the amplitude squared. So you get an expression here for the gravitational wave intensity that looks much like the intensity for electromagnetic waves in terms of the electric field amplitude. So it's, again, a very nice parallel, which I'll keep on emphasizing these nice parallels here. All right, so I'm going to go ahead and talk about quantizing the linearized GR field. So we're going in the direction of classical to quantum, hence you got the classical waves over here becoming essentially gravitons over there. And that starts with quantizing the metric perturbation. Again, just keeping in mind, this is weak gravity. So this is the perturbation that came out of linearized GR. And I'll just mention a little bit about this. I'm not the first to write this down by any means. It's found in a lot of papers. Grishchuk has worked on this considerably. I think there's like 5 papers in there in that span of time. And Carney's a more recent place where you can find this expression. So you'll notice that the prefactors here are chosen in a very particular way. That is something I noticed varies in the literature. And I'll show why it's very important, in my opinion, to have the prefactors exactly as they are here, with the 4 pi c over omega, and then particularly the Planck length out there in front, because that's how we're going to recover the Isaacson power formula in the appropriate limit. So I'll just mention that these Xi tensors are just the polarization tensors, and the B hat is the annihilation, and you got the corresponding creation operators. Very analogous to what we have in electromagnetism when we quantize the vector potential there. So it again also has a prefactor, and then you've got your polarization vectors and your creation annihilation operators. I distinguish the A's from the B's so that we don't confuse which apply to electromagnetism and which applies to gravity. All right, so we can go back to that electric-like and magnetic-like tensor field that we defined earlier, and we can write down quantized versions of them, just as using the definitions that I showed earlier, where the electric-like tensor is the time derivative of the perturbation, and the magnetic-like tensor is essentially a curl. Again, very analogous to the case in electromagnetism. So just standard QED here at the bottom of the screen by comparison to what we have at the top of the screen for the gravitational case. Now, here's where the analogy continues very beautifully, which is that if we start with the Einstein-Hilbert action, which is in terms of the Ricci scalar, and of course, kappa is just your Einstein constant there, you find that the linearized Lagrangian density for the transverse traceless perturbation, as seen in this bracket, can be written in terms of our electric-like and magnetic-like tensor fields. And Barnett showed this back in 2014. So this is not something new that I found. What I find to be interesting, let me also mention that it's obviously analogous to the Lagrangian density in electromagnetism, and also just to confirm that the Lagrangian is legitimate, we see that the Euler-Lagrange equation does return back the correct equation of motion, which is the Einstein field equation in vacuum. Now, what is new, I've never seen this in the literature, is that if we're going to apply a canonical quantization process, then we'll need a canonical momentum tensor. So the standard procedure is to take the derivative of the Lagrangian with respect to, in this case, the perturbation, the time derivative of the perturbation, and you get a result that is proportional to the electric-like tensor. Again, directly analogous to what happens in electromagnetism, where, again, the canonical momentum vector is proportional to the electric field vector. That's the same thing that happened here, except, of course, it's tensors. So we can plug in the electric-like tensor operator that we had on the previous screen, and so now we get a canonical momentum tensor operator. It's kind of a mouthful, but that I have not seen in the literature before. Now, the reason I think it's important is because now we can show that the perturbation operator and the canonical momentum operator satisfy uncertainty relations. And these can be shown from the operator expressions in the previous slides. And again, this is very analogous to what happens in electromagnetism as well. And then you can use a general uncertainty principle. You can find this, say, like in Griffith's textbook on quantum mechanics, where any two operators will satisfy this general uncertainty principle. Not general in the sense of GUP, as sometimes is talked about, like in terms of like Planck scale physics, but this general in the sense that any two operators will satisfy this. So if you use the two operators we have, namely the perturbation tensor and the canonical momentum, then you'll get this uncertainty relationship here, this uncertainty principle, which again is analogous to what you have in electromagnetism. So at this point, the framework is essentially complete. We have a nice quantized theory of gravity, but I remind you, this is only linearized general relativity, not full nonlinear general relativity, and we haven't introduced any kind of interaction terms with matter. So those are really actually the issues that end up causing problems when you try to quantize gravity. So honestly, the main reason why I found this framework to be very beautiful and helpful is because it, in my opinion, motivates the idea of still seeking a quantum theory of gravity, because it's shocking to me that linear gravity works so beautifully when you quantize it, and yet many theories out there claim that because we haven't found quantum gravity, then it's not a quantum field. Anyhow, so we can also define a Hamiltonian in the usual way, take a Legendre transformation in terms of the Lagrangian that we previously had, and you'll get a Hamiltonian that again has a very nice form, just like we have in electromagnetism with the electric field squared and magnetic field squared, except these are the tensor that we defined earlier. So it's analogous to electromagnetism, and then of course you can, as we did earlier, promote the fields to operators if you want to talk about a quantized theory and have a quantized Hamiltonian. Okay, so as I said, it's interesting to see that you can go in the opposite direction, and there's much to learn. It's not trivial at all, because if you go from gravitons to classical gravitational waves, you have to make sure that your quantum theory correctly reproduces classical GR. So in doing that, what you can do is take the electric and magnetic tensor fields, square them, because you're basically going to go after an energy. Square, of course, really means modulus squared. And then combine them together, and you get an energy density that basically is in terms of a sum of modes. And you might notice it's, again, very analogous to the case in electromagnetism. If you perform that same recipe, you'll arrive at an expression that's also the sum over modes, with the plus half being your vacuum energy, and then your number, in this case, the graviton number is the, in terms of the creation annihilation graviton operators, and then likewise in the electromagnetic case, it would be the photon number. So again, direct analogy between the two of them. Now, to make our way back to classical GR, what we could do basically now is realize that from that expression we just obtained, recognizing that, say, for a gravitational wave where the electric and magnetic tensor fields are related by C, just like they are in electromagnetism in vacuum, then we find that the intensity obtained by taking this energy density times C gives us this expression, which you might notice we have officially recovered the Isaacson power formula I had on an earlier slide, but now we have this expression here that we can also make use of and find that the intensity is actually the sum over all the graviton modes. So we've successfully shown the connection between classical and quantum theory of gravitational waves. So basically, this gives us confidence that our quantized procedure is correct, because you can essentially loop back again. So here's a nice little visualization. Came out of Gemini. We were just talking about this backstage about AI and all the beautiful benefits that we get out of it. And this is one of them. I just kind of asked AI, oh, you know, show me a visualization of the electric like and magnetic like tensor fields. Honestly, this is more just like an illustration. It's not really technical, but it's just a nice demonstration of the fact that you get a smooth waveform in the continuum limit of many quantized graviton modes, which I'll demonstrate that mathematically as well. One more item here, though, which is that the quantized Hamiltonian is also a sum of quantum harmonic oscillators. And so what you obtain is the standard quantum harmonic oscillator energy spectrum. So just as you do in the case of quantized electrodynamics, QED, the same thing happens here as well. So everything matches very nicely. Okay, so this is a nice little bridge in a sense. Literally, it's a bridge between classical and quantum. And this is a segue into the role of the Bohr Correspondence Principle. So this was actually the starting point that I was working on with some students, which is how to connect classical and quantum electromagnetism in a manner that it would be understandable even at the introductory level. And the idea basically is Bohr taught us that, as it states here, a quantum system becomes a macroscopic classical system in the limit as quantum numbers, such as photon number, become large. And of course, there's a reference here back nearly basically 100 years ago now, practically, that Bohr taught us this. So the motivation here was that in very, very introductory physics, like undergrad intro physics, we learned that the energy associated with an electromagnetic wave depends on the amplitude. But then we also learned later that the energy depends on the frequency. And so it's kind of interesting because it might make you think, well, wait a minute, is it amplitude or is it frequency? And that's kind of a seeming paradox, especially if you were to think of one photon, and that's where the problem arises, where if you think, okay, well, if I have one photon, I just set n equal to 1, but that would imply that somehow there's a amplitude to a single photon, and that amplitude is proportional to the frequency, which would make no sense, because amplitude we know has to do with how bright the light is, and frequency has to do with, say, what color. And it makes no sense to say that the brightness and the color are somehow linked in a way that if you adjust one, it necessarily adjusts the other. It would be like if I tried to do a dimmer switch in my kitchen, the light would necessarily go from bluish to reddish. It wouldn't make much sense. So we kind of tackled that. We really wanted to make sure we correctly understood the physics there so that we could apply it to gravity properly. I'll probably move through this a little bit swiftly because it's a little bit more technical and not as visual. But basically, again, in most standard textbooks on these topics, you can find that in K space, as it's called, which is these are the wave vector components in the x, y, and z direction. In K space, you have like essentially a differential volume, and if you think of it in spherical type coordinates, then it's this 4 pi k squared dk integrated. And so what you could do is write down that volume in terms of the 2 pi over the appropriate length for each of these wave vectors. And then what's commonly defined is the volume in K space, sometimes called the mode volume, is what I'm defining as V tilde there. So the purpose of this is that if you equate the two expressions that we have for the volume here, you equate those two together, you get this result here. And if you just divide by basically the left side or whatnot, and you could write it in terms of essentially a conversion factor is how I like to think of it as. And so this is the standard procedure to go from the summation of a function in K space to an integral of that function in K space. So again, standard formulation. But I think it's often overlooked that this is the secret sauce to the Bohr Correspondence Principle, that connection between quantum and classical. And the reason is because what happens is when you integrate, as most of us know, if you've taken some elementary calculus, that when you integrate, you're essentially taking the limit, visually speaking, going from left to right with these graphs, you're taking the limit as your curve is approximated better and better when you have more and more rectangles, which means, of course, the widths of those rectangles become smaller and smaller, and you have more and more of them. And so in this context, the width is essentially a frequency width. You could almost call it like a bandwidth, I guess. It's a frequency width. And so as you take the limit as m goes to infinity, where m is the number of rectangles, and thereby the widths get smaller and smaller, that's essentially how we perform the limit of the Riemann sum to get our integral. So this is just the fundamental theorem of calculus here. But from a physics point of view, it's very important because each of these subdivisions here has some photon or photons occupying it. Otherwise, the function is discontinuous. So what that means is that that integral, that process of going from summation to integral, is essentially the limit of large number of photons. So when you perform that integral, you are essentially invoking the Bohr Correspondence Principle. You're generating a classical model from a quantized model. You're going from discrete, quantized in a summation, to continuous in a integral. So you're invoking the Bohr Correspondence Principle mathematically, whether recognized or not. And I like pictures and analogies, and one of my students came up with this one. I thought it was really nice. I thought it kind of drives home the point in case the math doesn't sit well for you. Think of a photon as like a single bird. Okay, so if there was just one lonely photon out there, it's just like one bird flying in the sky. And the idea is basically that we know that when you have a multitude of birds, they produce flight formations like this V here, right? I see the birds flock over my house sometimes in this V formation, and I'm just glad my car's not parked outside. But anyways, so you got this V formation. The point is that with a single bird, you would never know that such structure formation exists. In fact, look at when you have a large multitude of them, you can't even tell that they're birds anymore. It's just like this cloud with structure associated with it. So I really like this analogy because it takes us from a single photon to a summation. See how they're still discrete, you can count them, to an integral where it's continuous. You can't even count individual birds there anymore, just as the case with the integral where it becomes continuous. So we go essentially from a single photon to a photon gas, if you will, to an electromagnetic wave, which is continuous. And so that really does resolve the paradox, that the seeming paradox between frequency and amplitude seeming to be interdependent, because what has happened now basically is that when the summation turned into an integral, and by the way, we tend to drop the vacuum energy term because remember, n has to be large, lots of photons or gravitons, and therefore the plus half becomes negligible. So that's another classicalization that's happening. The vacuum energy contribution becomes negligible. And so in that case, now we have successfully recovered classical field theory from a quantized theory. And this applies to the electromagnetic case as it does to the gravitational case. Okay, so with all that said, now if we go back and specifically talk about what's happening with the gravitational case, so I'm back to the tensor field there. What we can do basically is recognize, okay, if you add up all the graviton, all the energy of all your gravitons, and you relate that to the expression we obtained from the quantum theory, then you can show basically that the mode volume is related to the physical volume by this expression, essentially just by equating this equation up here to this equation down there, and you'll find that basically you arrive there. Now, what that tells us basically is that when the mode volume is essentially the same as the physical volume, that's only true when n is much larger than a half. So in other words, again, for large photon or graviton number. So that's why in many books, it's unfortunate this is not generally shown. In many books, the mode volume and the physical volume are assumed to be the same, but that's because the classical limit is already being invoked there, essentially. Okay, so one more interesting connection I'd like to throw out there before I kind of move on from this topic, which is for a single mode, you can write down the electric tensor field squared like this. And from the quantized operator expression, there was also a prefactor there that I had mentioned is very important. And you can take those two and relate the classical and the quantum to arrive essentially at these expressions that you see right here. And the reason those are important, in my opinion, is because now we have a direct connection between the classical amplitude that's on the left side of the expression and the quantized and the amplitude of the quantum field, the operator field. And notice that it is in terms of the number of particles, photons or gravitons. And this is directly analogous to what we find in QED. In QED, the same thing happens there as well. You can relate the classical and the quantum amplitudes by those expressions. Now, it's interesting. I noticed in the literature, I've only found one paper that did something like this, and there was a prefactor of 2 there instead of a 4. And the reason is because of not being careful to make sure we recover the classical Isaacson power formula. So if we're going to make sure everything's self-consistent, the prefactors really don't come out exactly the same for the electromagnetic and gravitational cases. Okay, and this is just a little visual of what a graviton like wave packet would look like essentially. So again, just a nice little visual that Gemini produced for me there. And I particularly love this image, and I got to give props to my student Diego Hidalgo, who created this on Gemini. It's a nice, beautiful, it's almost like mesmerizing in my eyes. I love the colors. And it just shows you the interconnection between the quantum theory and the classical theory. So notice that if you want to go from classical to quantum, then you're going to promote your fields to operators. You're going to get an uncertainty relation. And then if you want to come back to classical, then you have to sum over all the modes, and that brings you back to classical. And then in the middle is the overall connection between classical and quantum amplitudes. So I really enjoyed this graphic because it's a grand finale in a sense of the whole framework that we had been developing. Okay, so there's a couple of papers we're working on. This is the one that deals with the quantum electrodynamics and the Bohr Correspondence Principle. And you can see there's a number of students who are working with me. I mentioned Diego, and there's also Zach Gosef and several other students who have worked with me on this. And there's a second paper where we apply all of this to gravity, particularly essentially quantum gravity from linearized general relativity, with many of the same co-authors there. So we do hope to get those finalized and put out there as soon as we can. Oh, so there's a bunch of applications that come out of this framework that I just don't have time to talk about because I'm going to focus on propulsion, of course, for our APEC community. But we go into a number of interesting directions. You can quantitatively show the nature of quantum spacetime foam with this formulation, because you see how those quantized electric-like tensor fields, it's the vacuum state that is essentially giving you quantum spacetime foam. You can also show the nature of gravitationally bound neutrons, and we didn't make this up. Actually, there's a paper by Germain Tobar and co-authors on mass energy equivalence and gravitationally bound quantum states of the neutron. So it's essentially like these gravitational atoms, I call them, because they're gravitationally bound instead of electromagnetically bound. And so you can apply this formalism in that context there as well. We looked at photon-graviton gas models to see if we could characterize what the effective volume of a photon or a graviton would be in such a model. We developed a Stephan's law. Interestingly, it comes out very much the same as in the case of electromagnetism. A Schwinger effect. There's a gravitational version of the Schwinger effect. And most important for this talk, there's a gravitational Casimir effect. And that actually deserves essentially a whole talk on its own. I will discuss the Casimir effect at some length in this talk, but only in the context of how it might connect to tunneling and maybe even warp drives. But this is that's a topic that's near and dear to my heart. I'm very fond of it, and I do hope maybe I can talk more about that on a future occasion. Okay, so in order to have a gravitational Casimir effect, you have to have reflection of gravitational waves. And I did show quantitatively that you can potentially get reflection of gravitational waves from a superconductor if you introduce an appropriate electromagnetic field as well. So this is work that I've worked on. We actually, at Texas Space, we developed a patent on this. That's why I have the disclaimer at the bottom of each of my slides. There has been some debacles over this matter. Some other individuals attempted to publish this content ahead of us, actually, even though we have a patent on it, and that's turned into a whole dispute. But that's, you know, that's a sad story for a sad day, and we're having a happy day today. So I do want to just simply mention this, that there is a formal framework for showing the reflection of gravitational waves. Now, the reason, as I mentioned, that matters is because the Casimir effect would depend on that. So you can have things like cavity modes, or you could even have tunneling when you talk about the interaction of gravitational waves with materials, such as a superconductor. So these are just reminders of how cavity modes would look. You have these various modes that could exist. You could have tunneling here. This is in terms of a wave function, like in a Schrodinger equation. But remember that we quantize the gravitational field, so we can also look at things of this nature as well. So maybe a little reminder, when you have the Schrodinger equation, you can calculate a tunneling probability. You have an incident wave and a reflected wave and a transmitted wave. And when you go through the calculation, you get this nasty expression in terms of the hyperbolic sign and so forth. Usually we take an approximation of a small barrier. And so this expression cleans up quite a bit. But the main thing I want to point out is this. In typical undergrad textbooks, you'll see the tunneling expression like this boxed equation where another approximation is made that the energy of the particle is much less than the potential barrier. The main point is you notice that exponential decay there. So quantum tunneling involves an exponential decay factor that involves the barrier width, L, and the potential energy, U. Keep that in mind, because I'm going to make a connection with that when talking about the gravitational wave version of quantum tunneling. So many of us know about the Casimir effect, and a common heuristic description of it involves the whole idea that you've got these virtual photons that exist in the vacuum, and there's a quantized number of modes that you could have between the two plates because of the reflective boundaries only allow a certain countable number. It's an infinite number of modes, but they're countable, whereas outside the plates, there's no such boundaries. And so there's also an infinite number of modes, but they're, I guess, not countable. I'm trying to use math language. But the point is that you have more modes outside the plates than you have inside the plates. And as a result of that, you get this inward pressure that's understood as the Casimir force. Now, I mentioned that this is essentially a heuristic description because notice there was no math there. And generally speaking, when the Casimir effect is calculated, it's not done following this recipe that was just described. The reality is generally that when you do the calculation, I actually had it on an earlier screen where the energy involves an integral over modes. So what you do basically is you recognize that there are essentially evanescent vacuum modes across the gap, and notice that exponential decay that comes in, which means this has the same mathematical formality as quantum tunneling. It's the same formalism. What's going on here is the kappa is essentially involves the modes that exist between the two plates, where omega is the imaginary frequency, and these are the longitudinal modes that you have there. So basically what's going on is, as I mentioned here, you could think of it as like a vacuum fluctuations leaking between the plates and overlapping their evanescent mode tails across the gap. And then after multiple reflections, if you want to think of it as like round trips, you basically have standing waves in there, because as we know, traveling waves reflecting off boundaries, you end up with a standing wave. And that is essentially what causes the Casimir force. And so I'm just trying to point out that there is an important connection between tunneling, essentially. Evanescent mode tails are essentially like tunneling. The only difference, we call it tunneling when it's a particle, because we don't expect it to go through a barrier, whereas waves we do expect to go through barriers. I can tell you that because when my kids are yelling in their bedroom, I sure hear it, because those are sound waves, right? But if they're throwing the ball, it doesn't land on me because it hits the wall, right? Particles and waves are different in our classical world, but here in this context, tunneling occurs because we know particles act quantum mechanically. So I'm just trying to make the connection between tunneling and Casimir effect. So we can apply that then to the gravitational case. I mentioned a little earlier in the talk that it can be shown that superconductors act as gravitational wave reflectors. So that would mean that, from a heuristic point of view, you could think of it as virtual gravitons that are bound inside there. But again, from a more formal point of view, using the evanescent wave modes, then you can see that you are in fact going to get a gravitational Casimir effect from the quantized gravitational modes that exist in there. And I think this is very much connected, of course, to the fact that I already showed you can quantize gravity, at least linearize GR, which to me, it makes it convincing that this gravitational Casimir effect would indeed exist. So in principle, you can control boundaries. Like, for instance, the dynamical Casimir effect has been proposed before. I'm unaware of it ever having actually been measured or demonstrated, but in principle, it exists. So we've looked at this. I work with Professor Raymond Chow. He was my PhD advisor, and he's an expert in quantum optics. And we've looked at this whole idea of a triple Fabry-Perot parametric oscillator and whether it could be used to transduce and amplify electromagnetic and gravitational waves. And so this whole idea of controlling the boundary conditions is what I'm trying to emphasize here as a possible important feature of this framework. So a example of controlling quantum tunneling, which I already showed is connected to the Casimir effect, is in the scanning tunneling microscope, for instance. So tunneling is essentially controlled because, as I described here, you got the electrical conducting probe with a very sharp tip is brought near the surface, and there's a vacuum gap, acts as a potential barrier there. And so basically by essentially scanning over a surface, then the tunneling produces essentially a tunneling current that could be measured. And so then the surface can be mapped out via quantum tunneling. So in a sense, I would argue that this is a controlled quantum tunneling because you're determining essentially the distance that you have there and whether quantum tunneling occurs or not. So controlling quantum tunneling is not unheard of at all. It's effectively what's going on in this technology that, of course, already exists. So this is where I get a little speculative. Okay, so full disclaimer, not claiming that this is rigorously developed. This is where I kind of go out on a limb and try to make some connections between all the things that I just talked about. So we know that the classical warp drive is typically described in terms of metric engineering. So the whole idea basically is that you need to have a certain energy distribution, typically involves a negative energy density and a positive energy density, and things are arranged in such a way that you produce this bubble. You have essentially a propulsion because space is being compressed on one side and expanded on the other. But the whole problem generally is that there's a need for negative, or sometimes called exotic, mass energy, essentially. So that tends to usually be, as far as I'm aware, I'm not an expert in warp drives, but that tends to typically be sort of the deal breaker for trying to make this actually happen. I did correspond with my colleague, Dr. Jose Rodal. He just published a paper, actually, you'll notice here at the very bottom here, a warp drive with predominantly positive invariant energy density and global Hawking-Ellis type 1. So he's been working on this topic a lot, and I asked him actually to help me tailor this slide, and he did exactly that, which I appreciate very much. So you'll notice that in references 1 and 2 here, claim to reduce exotic matter by engineering an effective kappa, which is the Einstein constant, as not essentially a constant, but rather dependent on material via metamaterials. So Jose Rodal argues that this violates conservation of stress energy tensor if non-dynamical, and is experimentally excluded in any viable scalar tensor completion. So, and then there's more technical details here. Honestly, I'll defer to Dr. Rodal for more details on this if anyone's interested in this. But the main reason I included this in my talk here is to show that we know the classical warp drive has problems associated with it. It looks like Dr. Rodal has made progress. I did notice that it's predominantly positive invariant energy density. So perhaps he'll elaborate on this one day for us if he joins us at one of these meetings. But I get the impression that this isn't ultimately the grand finale of the whole thing as far as warp drives being achievable. So what I'm suggesting is maybe there's an alternative. And this is where I said I'm going to get very speculative. And the whole idea would basically be this. I've already shown the connection between quantum tunneling and the quantized gravitational field. So what if a warp drive could be produced via probability field engineering? In other words, the gravitational quantum tunneling. And I do thank Gemini for this image. I'm not going to lie. It makes really cool pictures, and it even labels them for you. Look at that engineered probability field surrounding the Starship tunneler. So it does a great job, like reading your mind sometimes. Like I was like, that's perfect. That's exactly what I want to have. So as I state here, the quantized linear GR perturbation implies that metric engineering is equivalent to probability field engineering. Could this make it possible to control quantum tunneling and use it as a type of warp drive? So the idea, very speculative, possibly the idea of engineering quantum probability field to control quantum tunneling through the space-time barrier. So I was kind of picturing it like the STM, the scanning tunneling microscope, that in a sense the barrier here is essentially crossing space-time. And so if there's a tunneling in a sense that's possible through space-time itself, perhaps quantum tunneling is in fact the way that could be achieved. Now, it did remind me of the ER-EPR conjecture, because in a sense that's also a connection between a quantum phenomena, namely entanglement, and a classical phenomena, namely a wormhole. So there's a very nice table here kind of mapping out the parallels between those two. And as far as I'm aware, the holographic principle, to my knowledge, is the only formalization of that idea that I'm aware of. In other words, really putting math to the idea, not just simply imagining it, but formally writing it down in a way that is consistent. So you'll notice that quantum tunneling probability is given by the probability, the transmission coefficient T in terms of the action, particularly the Euclidean action. So I did learn quite a bit as I was going through this to distinguish the Lorentz action and the Euclidean action. So going back now to the action that I wrote early on in the set of slides, the Einstein-Hilbert action, again linearizing it. So I already showed all of this, and that it's analogous to the electromagnetic case. So now perform a Wick rotation, which involves a transformation of time to imaginary time. So the Lorentzian action becomes the Euclidean action, and then the general expression for tunneling becomes this, with notice there's no I there anymore. But now you have to work with the so-called Euclidean Lagrangian, and you find that because of that transformation, you pick up a sign change in the Lagrangian, whether it's for the electromagnetic case or for the gravitational case. So take it for whatever it is. I'm suggesting that this is at least a start to a formal mathematical framework showing that perhaps quantum tunneling of the quantized gravitational wave field is possible, at least the linearized GR field, and perhaps that could play some role in the context of warp drives, for instance. Now, as most of us probably know, the ER equals EPR conjecture really has to do with the Einstein-Rosen bridge, wormhole, and the Einstein-Podolsky-Rosen entanglement, and that basically they may be one and the same thing. Now, what I'm suggesting is there could be even more connection than that. For instance, you'll notice here that the ER equals EPR conjecture, which is connected to quantum entanglement, but I just showed essentially that there's also the role of quantum tunneling involved here. And, just to fill out the image, I thought, what else is related? Well, quantum teleportation. So interestingly, perhaps there's some sort of interconnection between these different phenomena that would all play a role. Because after all, they all involve non-locality, or what Einstein called spooky action at a distance. So again, just an interesting food for thought in connecting all these ideas together. Now, there are essentially already quantum entanglement experiments that have certainly been done in the lab. And so if quantum entanglement really is truly connected to wormholes, maybe that there has been non-traversable space-time bridges already developed in the lab, but just not practical for any kind of actual warp drive or space-time travel that we would be interested in with spacecraft. Now, I did take some time to look up as best I could topics on, see if if these ideas have been looked at in the literature. I found this document, it's from 2004. So I imagine the APEC community probably is aware of this. I was not. I found it to be an extremely interesting paper because it really actually summarizes like all these ideas in one nice, neat packaged paper. By Mark Millis, Prospects for Breakthrough Propulsion from Physics, here associated with NASA. So it says space drives, warp drives, and wormholes. These concepts may sound like science fiction, but they are being written about in reputable journals. To assess the implications of these emerging prospects for future spaceflight, NASA supported the Breakthrough Propulsion Physics Project from 1996 to 2002. This project has 3 grand challenges: discover propulsion that eliminates the need for propellant, discover methods to achieve hyperfast travel, and discover breakthrough methods to power spacecraft. So I picked some highlights out of this that I thought were particularly relevant to what I've been talking about. Superluminal tunneling. Now, I had to mention this one because these references that are stated here, 3 through 5, reference 5, in fact, mentions Raymond Chow, who worked specifically on superluminal tunneling, faster than light, light that's faster than light, essentially. And so interestingly, that was in this paper that involved like kind of a listing of all the different possible avenues to propulsion. Then there's this exploring vacuum energy. So this includes the electromagnetic energy state of the space vacuum. It has been shown analytically and later experimentally that this vacuum energy can squeeze parallel plates together. That's the Casimir effect. So I had to mention this because clearly the Casimir effect is what I've been talking about. And I noticed Hal Puthoff is in the list of references here. In fact, I just was watching the whole Age of Disclosure documentary, extremely fascinating, and of course talks about some of this, and Hal Puthoff is in there. Metric engineering, kind of a buzzword that has come up quite a bit. Put down a number of the references that are discussing that. And so as I said, I'm suggesting perhaps there is an alternative to metric engineering in the framework I just described. And then I noticed this interesting section, private quantum vacuum research, gravity as a consequence of the quantum vacuum fluctuations. Again, Hal Puthoff involved there, and clearly connected to what I've been looking at, specifically gravity as a 0-point fluctuation force. So I'd like to summarize now. Basically, the main framework of what I described is how to take linearized GR and canonically quantize it in a manner directly analogous to quantum electrodynamics, apply the Bohr Correspondence Principle to provide a formal consistent bridge between classical and quantum fields. And then that gravitational wave reflection, which I didn't demonstrate, but I could on a future occasion, combined with quantized linear GR, which is what I was focused on in this talk, implies controlled gravitational Casimir forces. So that was pretty much the foundation of my talk. Then went into a little bit more speculative stuff, such as the fact that the Casimir effect is a form of vacuum tunneling, therefore controlled gravitational Casimir effect could imply controlled tunneling of the quantized gravitational field vacuum modes. and that the classical warp drive, which requires metric engineering, could have an alternative, namely a quantum tunneling warp drive using probability field engineering. And this is reminiscent of the classical quantum connection in the ER-EPR conjecture. So the classical warp drive, as we know, attempts to engineer the metric, but requires an exotic stress energy tensor, whereas the quantum warp drive would involve engineering the boundaries and states of the vacuum of the perturbation operator. That will modify the electromagnetic the stress tensor, and then back action or back reaction produces a space-time curvature that could involve essentially like a wormhole, if you will, or something that a warp drive would benefit from. So for acknowledgements, I'd like to thank Professor Raymond Chow for very helpful discussions, Professor Douglas Singleton, Professor Gerardo Munoz, Dr. Ahmed Farag Ali, Dr. Lance Williams, and Dr. Jose Rodal. I'd like to also very much thank Texas Space for support, and Tim Ventura and the APEC community for the opportunity to present this research. Thank you.
Wow, Nathan, that's amazing. Thank you, man. Thank you, thank you, thank you. Okay, here, let me take down, I'll take down the screen share. I'm going to bring everybody in. And guys, let's give an enormous applause to Dr. Nathan Inan.
Thank you.
Man, you are so much deeper on, I mean, the mathematics and the formalism of this than I ever possibly could be. What did catch me was the Casimir effect reference. It seems like that is just coming up again and again and again and again lately, you know?
Yep.
Yeah. Well, so our next up, we have Orestis Lazanakis. He is not on stage yet. I'm actually waiting. And so part of that is he's in Europe, right? So his time zone is completely different than ours. So it's possible that he just got his calendar wrong with it. But I did message him. And, you know, in the meantime, guys, do you have any questions? I mean, since we've got everybody up, do you have any questions for Nathan?
So, yes, Nathan, thank you very much for the presentation. It was very interesting.
Thank you.
So you were talking mostly with on-shell far field kind of stuff, right?
Yeah.
So because in the most warp drive discussions, the near field type of stuff is where people are trying to make it interesting or get to a result. So is that also included in your framework, or how do you deal with that?
That is a great question, Joel. And it's actually something that I have definitely thought about. You see, the interesting thing is that in gravity, as I was showing in my slides, it's that transverse traceless perturbation that is involved in gravitational waves. And so it's the natural choice to use that to then go to the quantized version to basically use the same formalism as quantum electrodynamics, right? Now, the thing is that in electromagnetism, we don't really have that issue of distinguishing between near and far fields because maybe if I actually, am I able to
Same as in the beginning, I guess. The share and the leave button got mixed up.
Oops. Yeah, okay. Wait, there he is. There he is.
You know what? It's killing me. Every time I go to hit share, I notice that it's not that red button. That's leave studio.
Oh, yeah.
So I got to hit the share button. So am I still able to share?
Yeah, just hit the share button and then it will.
Cool.
Yeah, there we go. And we'll give it a sec and then. Okay, so I will add that in. And this is the small version, but yeah, you can zoom in.
Yeah, I can fire it. So what I was mentioning to Joel is that it's right here at the bottom. I know it was, I didn't spend time on it, and I actually gave a whole talk on this. But the whole idea basically is this H00 and the H0I, those are the near fields that you could say, or they're what you would use to describe the near fields. Now, the thing is that they don't involve, gravitational waves don't involve those perturbation contributions. So in gravity, you have this interesting thing where everything gets decomposed into a scalar, a vector, and a tensor, and only the tensor piece is involved in gravitational waves, whereas the scalar and the vector are not. Compare that to electromagnetism, where you don't really have that issue. So right here, for instance, in electromagnetism, you see there how the magnetic field only involves the vector potential, and the electric field in this context only involves the vector potential as well. The only thing you don't have there is the scalar potential. But if you make a gauge choice, you can just simply eliminate it anyways. So interestingly, I'll try to make a long story as short as I can. In electromagnetism, you don't run into this issue of having to distinguish near and far field to talk about the Casimir effect. But in gravity, you do have to talk about near field and far field. And it's only the far field that acts as gravitons. The near field doesn't act as gravitons. And so you have to use the far field if you're going to talk about a Casimir effect. And then we saw that the Casimir effect leads us to, the role of vacuum energy and tunneling and warp drive and all of that. So I'm probably not giving you the most satisfying answer on the spot. I'm doing my best to try to give you a brief answer. But I would say the takeaway would be that, yes, you can deal with near fields, but they aren't going to ultimately describe vacuum energy. And so in that context, you're purely in classical. There's no bridge over to the quantum, because you have to use the far field, the wave field, to get to gravitons, to get to vacuum energy. Does that kind of make some sense?
Yeah, it kind of does. I'm not sure if you're aware, so I'm working in a framework developed by a German physicist Burkhard, which has extra dimensions, but not in the Yakuza Klein kind of style. And it actually has some of the ideas that you mentioned are in there. So you have a quantization, which I find interesting. So I would also ask to that point, do you have a fixed, let's say, limit, like a smallest area or line element or something? Is that a fixed number, or is it dependent on something? Or yes.
Oh, okay, so the closest I think I could get to addressing what you're asking about is some sort of like a minimum length scale, for instance, right?
Mm-hmm.
And it's so funny you asked that, because actually I really debated including that in my talk. And I was like, nah, nobody's going to ask me about that. And sure enough, you're asking me about it. So I can jump over here really quick to a talk that I gave connected directly to what I just showed us right now, but specifically getting into minimal length scale. And basically the idea was that there is essentially a GUP, or generalized uncertainty principle, that you could look at. Now, we know that the usual GUP involves a position momentum uncertainty. And so the purpose of GUP is to give us a minimum length scale naturally there. So if I were to elaborate more on what you're asking, it would be basically me sharing more of these slides, which I can do on a later occasion. But the whole idea basically is that if you take what I just showed for gravity, and see which involved essentially this uncertainty relation here, but you notice that I've now modified it with this extra term here, that will essentially give you a minimum. Now the problem though is this: because we're talking about quantized fields, it's not the position momentum uncertainty anymore. It's now a field canonical momentum uncertainty. And as a result, your minimum is no longer a minimum length. So this is something, so I guess my short answer would be, this is something we've been working on. I've actually been working on it with Professor Douglas Singleton. We took a look at this and we had some ideas. I gave a little mini talk on it, but we have yet to do more on it. So the short answer would be no, there is no currently established minimum length scale yet identified with that quantized theory, but it's quite possible there could be if we were to employ something like a GUP model. Does that make sense?
Yeah, interesting.
By the way, I'd love to know more about what you're doing. So maybe on a later occasion, if you want to send me any of your material, I'd love to. Yeah.
There are 2 HEIM presentations on APEC if you want to watch them.
You can see the private chat there is on the side of your screen share. You can see me negotiating with Jenny. So I think she's going to go in about half an hour. She's going to present in about half an hour.
Okay.
So yeah, no, it's totally cool.
Oh,
chaos.
Sorry, I'm exposing the private chat.
It's boring private chat. It's boring, right? So that's cool.
At least nobody's saying horrible things. That works out pretty good.
No, yeah, I'll say wonderful thing. Nathan is absolutely the best ever.
Looks like we have the comments here as well. Is that helpful for me to have here to
it's completely up to you. Yeah, if you want to scroll through them. I mean, it doesn't seem like it's causing any trouble, you know.
We don't have any
I'll tell you, so Nathan, if I actually have a question, if you're open to staying until like, you know, maybe another 25 minutes or so.
Yeah.
So I want to take things in a different direction, which will probably offend everybody in the chat. But so the big transformative thing for me this year is AI. And as we all know, Dr. Jack Sarfati has been completely transformed by Grok. So that is like playing a larger role. Now, one of the things that I've noticed is the physics community, the folks that I know who are doing physics, are having a more challenging time because the AI tools aren't as well developed, and it keeps bringing people back to Wolfram, right? Because I've done a lot of searches and it's like, okay, go back to Wolfram for it, you know?
Really?
But I wanted to ask, like, are you using this in your workflows at all yet? Or
oh,
is it still...
absolutely. Yeah. I don't mind showing what I do. In fact, if this is helpful, I'm happy to share specifically what I do. So I will develop material as you can see obviously in these slides, and then I'll go to AI and I'll ask for feedback. So like, for example, I'll put each of my slides in here and ask it what it thinks. Like, you know, I'll put in this slide and ask it, you know, if I have any mistakes, and it'll catch sign errors, you know, things of that nature, or help me understand things that I didn't before. So here, like, for example, it's talking about the wick rotation. It does make mistakes, as you just pointed out, though, because you see here, for example, it's saying that the wick rotation involves a minus, but in fact, I had the minus. So like, you know, you just got to be conscious of the fact that it's not perfect, right? So like, you know, over here, I actually had that in there already, and it just overlooked that. But there was other things it showed me about the distinction between the Lorentz and Euclidean Lagrangian. So right here, that was interesting information for me that I hadn't appreciated before. So definitely, and this is a very long thread, by the way, like, you know, all the way. I've been working on this for, you know, probably weeks there. So absolutely, it's fabulous. It just comes with caveats, though, as I'm sure you know, which is, obviously you want to check everything. You don't want to just put something down on a paper or in slides that you that you haven't developed yourself and understood. You don't want to just kind of migrate stuff over, because as we all know, it makes mistakes. The other thing is sometimes it doesn't think outside the box. So you have to kind of keep working with it, because it's kind of locked into traditional physics oftentimes. And I even spent a lot of time trying to ask it, like, what are the references you're using? And then it's very vague. Like, it just says, well, I was trained on general information on this topic. And I want to know, like, what books did you actually like? And so, you know, but on the other hand, by the way, sometimes it thinks outside the box too much. And you can almost, like, you know, I was just having an email exchange with some colleagues, you know, just yesterday, and they're like, if you beat it to death, it'll finally give up and tell you what you want. Like, you know, if you just keep telling it, like, well, let's assume that's true, then keep going. Okay, well, you know, even though you said that's wrong, still assume that one's true also, and keep going. And then all of a sudden, it's given you the theory you wanted to see, but that's because you forced it to.
Okay.
You know?
Yeah.
So those are my comments.
That is so awesome. I mean, I think, like, I feel like we are all kind of in over our heads with this in one way or another, you know, and like, I'm using it as a writing aid. And that was why I was really intrigued. I'm also really excited to see that you were using GPT, which is what I use. But again, Jack is using Grok, and GPT itself keeps pushing people back to, like, I've asked it, what's the best for physics? And it's like, Wolfram,
I did too, just yesterday. It said Wolfram. Actually,
that's what it came back to for me. Yeah. I was like, what's for engineering? And because the challenge that I'm seeing is, like, a lot of the folks that I know are looking at physics, engineering, computer-aided design, all sorts of stuff. And it's just not there yet for for so many of those things, you know?
It's funny you say that. I was literally just looking at this a couple days ago, and here's the little chart. Now, I don't know if chat's biased to itself. It could very well be, but here's what it claims is that supposedly when it comes to deep conceptual physics reasoning and step-by-step derivation, it's saying that, and I only have to compare those three.
ChatGPT is definitely the best. I've messed around with Grok, Gemini, GPT, then Gemini, and Grok is third in my opinion. Like just like
so in other words, this is accurate.
This is accurate. Yeah, it's accurate. Yeah. Definitely.
Mm-hmm. I agree.
Wolfram is integrated, I think, with ChatGPT. I don't have a version of Wolfram that's integrated.
Oh, interesting.
Yeah.
Really?
But well, yeah. If you buy the latest edition of Wolfram, it is integrated with an AI, which I believe is roughly ChatGPT.
Oh, well, I bought Chat. I mean, I think for $20 a month for Chat. Is that the same thing or no?
No, ChatGPT. I'm subscribed to ChatGPT. It is not Wolfram. But if you subscribe to Wolfram, it has AI capacity now, and it might be ChatGPT. I'm not sure. I need to check on that. I'm sorry.
Oh, so it's the other way. You need to be on Wolfram.
Get them to talk.
Yeah. But if you use ChatGPT, it will write code for Wolfram. So it's similar. If you have ChatGPT and if you have an old copy of Wolfram, you can kind of do it yourself, which is what I've done.
You're talking about like the LaTeX?
Yeah.
Oh, okay, so if I can ask for Wolfram, you're talking about Wolfram Alpha.
Yeah,
right?
yeah. I have Wolfram Alpha, Mathematica. I have a copy of Mathematica.
Okay, the reason I ask is so I'm just looking on the website and like I know we're kind of going off the rails, but I think that this is really relevant because these are the tools that we use. And so it's saying it's like I think $10 a month, something like that. That's not horrible.
So if you have the API for ChatGPT and you've paid like the paid version of Wolfram, you can get the API to invoke Wolfram as a tool.
Okay. And again, guys, I'm sorry for taking everybody off the rails. Jared Yates yelled at me. I think last time I did the same thing. I took maybe this was the open mic, but Jared was there and he's like, Tim, he's like, are we talking about propulsion or AI? And I'm like, well, it's a little of both,
it's kind of a little of both. Yeah. Okay. I might not have as many new slides because I've gotten so much into this talk, but maybe I'll
that's Jenny. It's totally cool. That's totally cool. I just appreciate your being flexible and being able to go a little early.
All right.
And again, Nathan, the Casimir thing really jumped out at me. That is so exciting to see references to that.
I knew you were interested in that. I am curious, by the way, are you guys all, I know we're going to switch over. I'm just curious real quick. Are you guys all aware of this document here by this Mark Millis? I assume this must be a staple in the APEC community because I referenced it in my slides because basically it hits every single aspect of propulsion ideas that I'm aware of that I've heard at APEC plenty. You talking about Jim Woodward and, this whole, and it's pretty short. It's like, 19 pages I see here. And it hits at all of the main topics I've seen. I wondered, have any of you seen this?
I have. And then with Mark Millis, interestingly, he did some presentations, I believe, at the STAFE conference and then later at Tony Robertson's SPECIF conference. So Mark was back in the day, right? He, I don't know if you remember.
2004 right here, so I'm sure much has happened since then.
Yeah, right. Mark, he was trying to do, like, they basically just, he was like a one-man army, right? They're like, okay, you do breakthrough propulsion for NASA. He's like, okay, who's going to help me? They're like, no, it's just you. You do it all.
Well, he was the co-author with Eric Davis on Breakthrough on Frontiers of Propulsion Science.
Yeah, he was what the backstory was. Bill Clinton went to speak on space something or other, right, in the 1990s, and it was in the same center as a Star Trek convention. And basically somebody said, hey, Mr. President, you're probably going to end up having to answer questions about warp drives. And so that led in a roundabout way to the NASA BPP program. And they did, I think they did have 2 or 3 people on it at one point, but Mark was the primary, and they just kind of threw him in the deep end. And they're like, okay, you know, we don't really have a ton of resources and we're not really sure what's out there, but you take it away and go for it. So.
Okay, so I actually.
Oh no, go right ahead. You ready to go?
Oh yeah, I was gonna say I'm ready to go, and I actually have. I found something I could do if I run out. Like if I.
Oh
I
yeah.
found,
Okay. Well.
I found something I could
Yeah,
do.
Jenny,
slides.
I see your presentation. So
right.
let's do this then. So Nathan, thank you so much, man. I honestly mean that. I love it that you are back. I love it that you're helping us close out the year. I would love to have you back in the future if you have more to share. I mean, you are doing real, like hardcore, high quality physics. It is absolutely amazing. So
thank you. Appreciate that very much.
Yeah. Well, so guys, let's put our hands together one more time for Dr. Nathan Inan.
Thank you.
Okay.
And
I'll
again,
be right.
thank you so much.
I'll be right back. 1 second.
Okay. And then, yeah, when Jenny is back, we'll do her presentation. I should apologize to everybody for bumps along the road. Orestis I've been communicating with him. He is around, but again, he's like, I think 8 or 10 hours ahead of us. So,
all right,
you know, that and this time of year is always a challenge. Yeah, okay, so let me do this. I'm going to take everybody out. And Jenny, thank you so much. So this is a continuation of your last presentation, right?
I'm going to reintroduce the ideas because last time we had so many technical difficulties that it just wasn't very conducive to sharing the ideas. And then I'm going to talk a little bit about some of the things that we talked about in the lab. Oops. Oh, what happened to my video? Something went froze.
Oh, it went blank for a moment, but
yeah, I don't know what happened there. That's so weird. But I think that the technical glitches we had last time were not conducive to sharing the ideas effectively. So this time we'll get these ideas out. Hopefully, yeah. And
absolutely, yeah. I would say,
yeah, and also
go for it.
Yeah, and also
I was going to say we're sorry. We do have some time delay. You know, so we are so close to the Christmas holiday. Well, I think that we have a little bit of extra time. It's a little more mellow. It's a little more flexible. So yeah, I would say go for it. Whatever, whatever time you need or anything.
And then I wanted to talk a little bit about some stuff that Dan and I were discussing. Dan from here. His last name is escaping me, which is ridiculous. And then I wanted to talk a little bit about some work I was doing on time more generally, which is kind of a return to my roots that I just got back into this week. And then which I think was kind of inspired by Dan here. Okay, so here's topological torsion drive. Yeah, so topological torsion drives and warp bubble physics. So last time I came here to talk about topological torsion, which was inspired by this paper that I was looking at way back in like it must have been like 2017, 2016. I found this paper by this guy named Barger, and it's a paper about cavitation research. And when I saw it, I was in one of these kind of late night, up late conspiratorial mindsets. I was like, whoa, this looks pretty Philadelphia experimentish. That was the mindset I was in. But, it's really pretty much just a standard propeller nuclear power sort of experiment where they wanted to understand what water does when it's under certain vibratory conditions, how there are these spaces that develop in the water where there's no water, where there's just absence of water. But the water in this case is doing something strange. Going to my next slide. So let's talk about what is this strange thing? What is cavitation? So cavitation is what happens when a liquid is locally pulled apart by pressure. So it's so violent that it forms vapor pockets or voids. So you think rapid pressure drop, the liquid can't hold itself together, micro bubbles form and collapse, enormous energy release in a tiny region. So there's ultra fast shock structures, wild symmetry patterns. And anyway, this happens behind boat propellers and ultrasonic cleaners, in bubble jets, around hydrofoils. And anyway, but in acoustic cavitation, the driver is sound or some kind of vibration. Vibration meaning sound, basically. It's the same thing in matter. So anyway, in 1964, this guy named Barger, James Barger, He was incidentally the acoustics guy who studied the JFK assassination. I found that kind of interesting. Anyway, he performed this high-speed flash photography study of spherical cavitation from a pulsed acoustic driver. And Mark bought a snow globe. We should maybe Mark will be here and talk about what he's done with the snow globe. But instead of like from a diffuse source, he had a pulsed source, a single pulse source. So there's a point-like transducer. It emits a single high-pressure acoustic pulse into the sphere. The medium experiences a sharp compressive front, and then this triggers a formation of a spherical bubble. The bubble expands, stalls, collapses, rebounds, all spherical symmetry. But what they expected was one bubble, one empty space in the sphere. So one shock front of a empty space, like one circle where there was no water in it. But instead what they got was what from their perspective was absolute chaos. They got a central bright region and a set of nested discrete spherical shells like concentric circles expanding outward. Not 2, not 5, but 20 concentric shells. Not evenly spaced, they fell into 3 regimes of clusters with different spacing laws. So anyway, this was shocking at the time because there was no fluid equation that could explain this spacing of cavitation shells. It made no sense. So anyway, I found this fascinating when I looked at it, and it just stood out as just really weird to me and gave me the heebie-jeebies. And I still don't understand why this gave me the heebie-jeebies, because it's kind of just, it's acoustic physics, But, acoustics has a lot of weird, like classical physics is a lot more eerie and weird and space age than we give it credit for. Like, you can use acoustics to levitate the objects. You can use acoustics to do all kinds of wild stuff. Cymatics is just acoustics, So I think that we think of quantum physics as the domain of the weird, but lots of weird stuff happens in the classical realm, and we kind of shortchange ourselves a lot. But anyway, I thought this was really weird. But anyway, physicists expected just kind of a normal ripple, and then everything calms down, and that's not what we got. It was surprising. I don't need to go into why. But anyway, why were they not expected? I guess we'll go into why a little bit. This is the equation they use. It doesn't predict what we got if you use this equation. There's no classical mechanism for this recurrence of spaced shells like this. And the spacing follows 3 different laws, which implies like a power law or something. And that's not what you expect. It's nonlinear, which is like a power. So it's like, is it spherical Bessel modes? Is it nonlinear? Is it bubbles? Like, is it acoustic standing waves? But none of these quite work when you try to apply them. So you try Navier-Stokes, and that doesn't produce 20 shock fronts. You try Rayleigh-Plesset, and that doesn't work. You try spherical Bessel modes, that doesn't work. You try, you do the spherical Bessel modes would be like a traditional cymatic type equation, like when you do the vibrating plate or whatever, you would do that in a 3D sphere. Maybe they'll get some cymatic thing that just explains. No, it doesn't. So none of these classical things that we use to do all these patterns that we expect generate that. So what's going on? Well, just out of some kind of loony mood, I decided, well, what if we applied my paper to this? What if we tried TUFT? And anyway, so what's wild is suddenly it makes sense. So if the internal state of water includes a geometric or phase-like degree of freedom, a collapse event has discrete eigenmodes. And now this is just kind of weird here. So they would propagate as spherical pulses with quantized radii, limited spectral range, exactly 20 modes, believe it or not, and natural grouping into spacing regimes. So, it's because torsion couples to the water, and that with the pulsing creates these this spacing of spaced separations in the water. And it's a little weird to me to think about this, and I still am thinking about all this. And Jack says EM cavitation has nothing to do with Higgs bosons. I agree, Jack. No, I don't think so either. And, sounds like there's a detailed discussion going here in the background that I'm, yeah. But anyway, yeah. So no Higgs bosons. But what's going on here is something is happening. There is cavitation. You can get EM cavitation. That's more intense than this kind of cavitation. This is just regular acoustic pressure cavitation. But what's acoustics? Acoustics is just vibrating matter. Matter is just part of the same background stuff that's vibrating in space-time. It's just space-time vibrating. That's why it couples to space-time, because matter is just embedded in space-time. So you get the same stuff of torsion in the field. Well, okay, you might need to have some background on my theory. My theory is basically that space-time is basically this ripply hot vibration stuff. The hot vibration is like a bundle of fibers. These fibers have torsion. Gravity is torsion, essentially. Torsion is the main thing. It happens to have all these other properties of gravity that we normally associate with it. Torsion is kind of a weak property in comparison to the other things that we notice about gravity where we are, but it's still the primary defining thing of gravity, because it's a twist in the fiber that gives it all of its various properties, in my theory. So the basic thing here that's happening is that anytime you have matter doing anything, torsion is involved. And in this case, you're doing something that kicks up torsion and makes the torsion apparent. So, and I think that the way I'm talking about it sounds indefinite, and I wish I had come up with a better way of talking about this, because I feel like once you can talk about something to a third grader and make it make sense to the third grader, you really know how to talk about it. And I feel like I'm not quite there yet, and it's driving me crazy. But okay, the basic idea is that when the matter is vibrating in this way, something about the way it's vibrating here increases the twist. And the twisting, the vibration allows the twisting to be seen and visualized, and it comes up in these modes in the behavior. So you see the spacing that comes up as a result of the twist. And they're similar to cymatic modes that you see when you vibrate sand on a plate, and then you see the modes come up because of the spacing of the sand. These are modes that come up because of the spacing in the hot vibration. And it's hard to explain, and I'd need to put the hot vibration, I need to show all this stuff, and I need to have better visualizations of the hot vibration. And I hate that you have to rely on me to say, yeah, this is it. But rely on me for a minute and say, well, this is it. So I'll develop some better visualization tools. But here we go. We're going to look at the math a little bit. But that's the basic idea. So if the internal state of water includes the geometric or phase-like degree of freedom, there are these eigenmodes. So eigenmodes are basically modes that you get, like harmonics on this structure. So you get these harmonies that are sort of like resonances, and they propagate as spherical pulses with quantized radii, quantized like discrete radiuses, like discrete concentric circles with limited spectral range. There's 20. Natural grouping into regimes, so they come at specific ratios, and a quantized torsion or phase mode cascade. So you get a specific, they come in a certain range that kind of just show up in a certain like spectrum. Sometimes these words are like jargon, and I have a friend who's always saying, Jenny, you use this complex jargon, I don't know what it means. And sometimes it's like, God, how do I say what this means? Because I learned it in terms of maths. It's like, how do you put this into language? Okay, now what Barger actually saw. Well, we just did this. Hold on. So TUFT's physical picture of Barger. The water shell develops torsion-rich curvature. So that's what I was just talking about. Via molecular dipole alignment. So what you have is the molecules, the dipoles, like molecules have like the polar aspect. They align with that curvature. The collapse releases discrete torsion bursts, not continuous water pressure waves. So you have to deal with the molecule structure in combination with the torsion. these bursts propagate as spherical shells that follow this formula. Sorry, my touch screen. I forget I have a touch screen now. Just got a new computer. Each pulse compresses water and generates a visible density wave, and only 20 allowed torsion modes come up. So this is very interesting to me because nobody understood why 20. And now here's 20 right here. And Barger unintentionally photographed a torsion eigenmode cascade. So I think that what's ironic is we can kind of find in the past proofs of TUFT, my theory, that people found not knowing they were proving a later discovered theory. You often find this, like we had all kinds of things that implied aspects of relativity or aspects of quantum mechanics before we actually had those theories. We just didn't know that we were dealing with aspects of those theories until later. So now I'm saying let's go sci-fi. This is maybe how aliens are doing warp drive. If we allow ourselves to believe in aliens, here, we're right at home here. We believe in aliens here, right? So anyway, space-time manifold. In my world, in my world, everything is nonsense, like Alice. So we live in a 9-degree space-time with base CP4. What do I mean when I say this? I mean that there are 9 levels of degrees of freedom that particles use to move. I don't necessarily think that means that there are 9 worlds. I'm open to the idea that there may be infinite worlds, if that makes sense, infinite universes. I do think that the only kind of universe that will produce our world has these 9 degrees of freedom with this kind of, well, not necessarily just 9, but they have to have these 9 to have the level of physics we know about so far. There are probably forces that we don't grok yet that are even in our universe, but they're so minor that we haven't looked at them yet. There are probably particles that we don't know about yet, but they're so minor that it's like, I don't really care about particles that much beyond the electron. So I don't really, like, if I don't even know if it's responsible to predict another particle, because then they're going to build another frickin' multi-billionaire, trillionaire collider just to find my particle. And it's like, do I want to do that? So I haven't even predicted new particles because of that reason. I was like, I don't want to predict another particle. I might do it, but it's like, they're going to buy, you know what I mean? That's what I mean. So anyway, but so there's this mega infinite Hawk vibration. It's infinite, but you only need 9 shells to get the particles we know about so far and the forces we know about so far. With base CP4, what does that mean? Base CP4 just means that you have this interior world with even shells. So there's even shells and there's odd shells. The odd dimensional shells are where the fields live, and the even shells are where these connection spaces that are sort of like where entanglement can happen and where wormholes can happen. And those even shells are connection spaces. And the 4D is enough even shells to hold connection spaces for all the particles that we know about. Now, in reality, the connection space is probably infinite in the sense that it could hold every possible thing. And in reality, the fields is infinite in the sense that it could hold the odd space. It could hold every possible thing. But maybe it's not really infinite. And maybe that's a metaphysical question. I don't know if it's literally infinite. I'm just saying it could be, and it might not be. And I'm sticking to 9 because that's enough to account for the neutrinos. And I'm not worried about anything beyond the neutrinos right now. Maybe eventually I will be, but right now I'm not. So that's the universe to me, is those 9 dimensions that hold everything up through the neutrinos. And anyway, it has fiber S1, which just means a circular fiber, and it's a twisted circular fiber with a phase, which you can represent as E, the number E, to the I theta, which generates U1 electromagnetism. That's when I write EM, I mean electromagnetism, and temporal twists, which sounds weird. But these twists are time, they're timelines, world lines, and they're also EM field lines. And they're also, they're not quite field lines in the sense that we usually think of field lines. They're field lines in a slightly different way. And I get into that way in my paper, although some people might want to see me explain it differently, but I would if people want to talk about it. And also, they're gravity lines. So gravity is the twisting of the fiber. EM is the fiber itself essentially, and the world line is the fiber itself essentially. But I deal with the world line and the field line differently than the standard way. But it is what it is. So anyway, world lines are from, whoopsie, I just switched again because I forget it's a touch screen. Shoot. Anyway, so torsion is this long equation. I'm not going to pretend I even know how to say that out loud, but in TUFT, it's the fiber-induced contortion K equals 2T, which is the Inan form, this thing. Anyway, that links the EM torsion, which is what I was just saying, to the gravitational twist. So that's just the mathy way of what I was just saying. So EM torsion couples. So EM, so this is the fancy way of saying what a lot of people in the alternate gravity propulsion community have been saying for a long time is if we know how to manipulate the EM field, we would know how to modify the gravitational field. And I think it's true. In my theory, there's a connection between electricity and magnetism and gravity. And this is it. And I believe this is the correct combination. So if you manipulate E&M according to this formula, you should be modifying gravity. And so that's it. I believe it's it. So anyway, so this is the coupling. You induce global topological defects, Aharonov-Bohm-like phases in the bundle, but you're doing it to gravity. So you can modify space-time with E&M. So there you go. I'm pretty sure. I might be wrong, but I think this. I'd stake my reputation on it. I believe this is the case. So anyway, the cavitation experiment translates to creating topological voids, regions of zero linking in the world line bundle, the universal space-time bundle, via EM pumped torsion surrounded by a shell of high-density knotted flux. This isn't fluid-based, but bundle-based cavitation. So, but fluid-based cavitation is bundle-based cavitation. You know, I spewed a bunch of crap and I had the AI say what I said, and then sometimes it says it in a way I'm like, why did you say it that way, AI? Or whatever. But the point is, the bundle is what's doing it. It's not really the water that's cavitating, it's space-time that's cavitating, and the water is cavitating too. I'm wondering if is cavitating what I really, is that the verb? But anyway. So, step-by-step construction of a UAP warp drive. Assume a spherical UAP core with a water shell. So anyway, you have a UAP. The core is where you live and you work in your UAP. And then you have a shell, and you have a little shell around your UAP, and then you have water in that. And, you know, you and sometimes you think of the engine of a ship as one area of the ship, but really maybe it's not like there's just there's a ship and an engine, like the ship is the engine kind of. So anyway, you have this water shell around it with a thickness of like just 1/10 of a meter for dielectric containment and cavitation mediation. The water acts as a classical proxy for bundle density. So because it's you're cavitating the water as well as the bundle. The bundle meaning space-time. The water is you're using the water as your kind of way of working with space-time because matter is embedded in space-time, and you couple matter to space-time. Like you're coupled to space-time right now. We work with matter, but we're really dealing with space-time all the time. It's weird to think about that. It's like I remember I used to argue with my physicist friend. Like I was like, well, why is it that the ruler isn't expanding too as the universe expands? And he was like, well, because the ruler is sitting on top of space-time. And we would argue back and forth like this. And it's, of course, like you're not expanding too because matter is embedded in space-time, but not space-time. But you're still interacting with space-time in a deep way. But anyway, we'll keep going. So the water acts as a classical proxy for the bundle density. So you're not expanding, but you're still interacting with space-time. Use EM induction, not acoustics, to couple to torsion. So I was kind of right and kind of wrong. You are embedded in the torsion aspect, but you're not expanding. Weird, but whatever. To couple to torsion via the fibers churn, like you're embedded to gravity, like you're dragged along by gravity, yet you're not expanding. It's bothersome to me, but whatever. Via the Chern-Simons 3 form. Chern-Simons is just a thing about the kind of twist you have. Anyway, so you follow this thing, the wedge product A, dA plus 2, where A is the connection. The connection is this thing that you get that connects parts of the fiber bundle to other parts, lifted to the S9 bundle. Anyway, don't worry about the math so much. Just trust. Whoa, unless you're a math geek, just trust that you can get these mathematical features off of the topology of the bundle, and then check, like, look these things up later. Download my notes. I can send them to you if you need them, or I'm sure Tim has them. Then the core setup, the UAP nucleus, embed the sphere as a hot subvibration. This is the 3D version. Usually when you're working with 3D, you can use this unless you're worried about specific forces, that, like neutrinos, like they're not forces, but specific particles or forces that you need upper level shells for. Unless you're doing that, you can think about 3D to think about most 3D situations. So you represent a stable soliton, you inject seed torsion via a central coil. So instead of injecting via pressure or vibration, you apply a rotating EM field. You get torsion density from the EM. You pump this. You create a low density bundle core, and the cavitation. Sorry, I'm reading way too fast. It creates initial unlinking, cavitating a low-density bundle core. So you get these shells just like you do in the regular sphere, except it's in a shell instead. You're starting with a shell and then putting shells into the shell, which is a weird way of thinking about it. But you surround the core with deionized water shell. Water's molecular dipoles align with the EM fridges, creating a dielectric bundle sheath that stabilizes the defect. You induce shell cavitation. Like, this is kind of saying what I was just saying again. I don't know why I did it this way, sorry. And then TUFT couples. EM field lifts to the bundle connection. So it's not really lifting to the bundle, but it's like the EM field is the bundle connection already. But you can think about it that way, where shell permittivity amplifies the torsion. The shell's the core defect. This is a weird way of writing. I'm sorry. I'm going to redo these notes. Confining the unlinked region to spherical topology S3 void. Anyway, what does this mean? You get acoustic coupling. So it's acoustic, EM, well, okay, wait, hold on. Well, you actually even get acoustic coupling in the EM situation, but the EM is bigger. So if you compare acoustic to EM, the EM is a lot more energy. The strength is a lot more, and it becomes cosmological level warping. You get a warp drive with EM. So you get propulsion. You get EM propulsion, and it makes me think that this is what's going on. Like, I told this story last time. I'm not sure if it was hearable, audible. So my brother and my mom and my dad, they would watch this Eagle Cam, and one day they'd see weird things. And one day my brother was screaming, "Johnny, there's a UFO!" And like, I got in there, and then it was gone. My brother was like, "If you'd just been here, I could have proved there are UFOs." Well, the Eagle Cam happened to be at Catalina Bay. And so apparently there's this conspiracy, and not a conspiracy, there's a story that there are these ships that come in and out, and people see them, and they saw one. It's not a conspiracy, it's just people see them. But it's a rumor. But it's people really see them. It's anecdotal, whatever. But what I'm saying is people see this stuff. And everyone talks about it, but I haven't seen them, but I believe them. My brother's a great source. My parents saw it. It's real. But anyway, what I'm saying, it's funny how we're trained to talk about things like, "Oh, this isn't really true," but it's true. People see it. Anyway, that's a photo of one of these things that people see at Catalina Bay. I have reason to believe that's a true thing because it's similar to what my parents saw, what my brother saw. I mean, assuming this isn't just some weird phenomenon that people, it might be a ship, it might be an alien thing that's charging up in the water. Anyway, people always wondered, why do these things go under the water? Well, assuming it's not just some visual weird plasma weird thing, swamp gas, whatever. Maybe it's aliens, I'm not saying it's aliens, but it's aliens, Anyway, what I'm saying is, if there are extraterrestrials and they're coming and they're visiting, what do they need? Do they need plasma? Well, actually, they probably don't. They probably don't need plasma. They probably just need frickin' water. And maybe they visit us because we have a lot of frickin' water. So anyway, you just get, you get cavitation. you induce this line element where the contortion does this, shrinks radial geodesics, you get propulsion. The line element thing is similar. Dan is doing some work with a line element. He's interested in looking at how it looks when you combine. Well, I don't know if he wants me to talk too much about what he's doing yet. I'm sure he'd be okay with it, but he's looking a little bit about thinking about the hop vibration, which he was looking at independent of me, which is interesting because Maya Benowitz was into it, and he was looking at how that would compare to Everett's many worlds thing. And anyway, like I kind of look at many worlds in the sense that I think about many possibilities, but I don't treat them as actual worlds, but he does. And so anyway, we've been doing a collaboration on that recently. But anyway, so that might be helpful as a way of visualizing some of this stuff. He thinks so. And so anyway, but we've been working on that. Anyway, propulsion, asymmetric torsion pump, linking momentum. You get this momentum. And the resulting velocity is determined by torsion gradient efficiency and system geometry. And these are the kinds of equations that you get out of this thing. Oh, and the energy to do this, quite low. Like, I mean, I'm sure there will be ways of linking it to other parts of the machine that require more energy, but the basic EM drive only takes like AAA battery level energy, which is totally mind-bending for me. And I'm like, really? It only takes that low of an energy to get warp drive? And apparently, yeah, it doesn't take much energy at all. And it's funny because like when I first did these calculations, I was using Grok, and Grok was like, well, you need all this energy, and like it's like, and anyway, I showed Jack, and Jack was like, no, it's going to be a lot less energy. I was like, are you sure, Jack? Like, yeah. And so I read it, and and finally I figured out that Grok was using an estimate from some old paper that required dark energy and all this other stuff. I'm like, yeah, no, but it doesn't take much energy because you see, we don't need not dark energy. What's the word? Exotic energy. You don't need exotic energy in TUFT, and you don't need exotic energy in Jack's model either. And that's what's kind of incredible is like you're starting to realize that some of the assumptions that we made in the 80s or before were wrong, because we used to think that there were aspects of reality that couldn't be overcome unless we had to overcome some boundary limit, some boundary condition, but the boundary conditions just aren't there because reality is built, it's knit differently than we thought it was. Like in TUFT, the universe doesn't have the same hard limits that we thought were there before because of the fibers. The fibers are woven in such a way. It's similar to the concept of the quantum flux. Like we used to think that you'd have to have negative energy or exotic matter because we didn't understand that quantum flux itself creates some of the conditions that would allow you to do the things that we thought you needed exotic matter or negative energy density for. So you can think of that as a proxy for the fibers. The fiber waving actually allows you to overcome the same limits easily. Visser was kind of working on the same problem, but from the angle of the quantum flux, I think is my understanding. No, he's not here, so I hate summarizing other people's work for them, but that's sort of how I understood it. Anyway, is there an underwater base under the Southern California coast? So why water is the perfect alien medium? High dipole moment, strong EM coupling, water forms stable spherical cavitation bubbles. That means it couples to space-time. No need for high temperatures or plasma coupling. Now, I do think plasma is probably helpful, and plasma I think will happen on the outside of this thing, regardless. Once it's moving, I think there's going to be plasma, but I haven't really looked into that yet. But I have that feeling knee-jerk that their plasma is going to build up around this thing. Okay, what the Barger experiment really demonstrates: a spherical collapse does not produce a single shock; it has a discrete spectral cascade. The collapse does mode dumping. The inner shells are high torsion curvature. The middle shells are intermediate. The outer shells are wrong range torsion bleed off. It's a topological event. Aliens don't care about the fluid. They want the torsion cascade. Water helps them do that, or at least visualize it when they're doing it. The goal is to exceed this threshold. The Barger style cavitation collapse, the U1 pumping. Here's how the pieces fit. basically it's just that matter is coupled to space-time automatically. It's embedded in it. And so if you do something to matter, you are interacting with space-time automatically because it's glued to space-time. So if you do something to matter, you're interacting with space-time. You're interacting with the torsion. And so that's what the aliens, if there are aliens, are doing, and why they like water, in my opinion, why they're in Catalina Bay. And I don't think that this means that they are an underwater civilization. I think it means that if they are from Cygnus A or whatever, if they're from Alpha Centauri, you know, they like Earth because we have water and we're a charging station. And they might do other things while they're here. Oh, look at those weird animals. Let's go check them out. Let's put a radio collar on them. Let's inject them with this and see what, you know, whatever. So, like, I think that you can model aliens as Earth scientists pretty well. Like, what do we do when we find some chimps? We watch them. We don't want to go up and talk to the chimps. Oh, hey, chimp, take me to your leader. No, we don't do that. We watch them and we radio collar them and we observe them and we try to understand them, but we don't usually go and try to make friends unless we're Jane Goodall, you know. And Jane Goodall was thought of as pretty weird at the time. So how an alien amplifies torsion using EM pumping. The goal is to exceed this threshold. EM U1 pumping provides phase bias in the fiber. You pre-twist the S1 fiber. You set the sign of torsion. Anyway, I really find it difficult to teach topology at this level in these talks because topology is very advanced math, and most of us, even me, have not taught it before. So I don't even know how to say a lot of what I'm saying. But the cavitation, because I've read this stuff. I didn't take a topology class where I heard people say this stuff. I just read it. Anyway, the cavitation collapse supplies the torsion spike. Combined effect of topological support to torsion burst, the coherent torsion modes, and I have a migraine right now, so that makes it really fun. Constructive phase summation, the spherical symmetric torsion wave fronts, all this stuff happens. And this is the summed amplitude of this whole thing. And because EM pumping sets all of the phi ends, you get maximal constructive interference. Okay, so you're getting coherence here of interference, which is great. So you want coherence. You want all the phases to line up. That's constructive interference. So the burst crosses this maximum torsion. So you get coherent torsion. And this flips the S1 fiber identification into a freaking wormhole throat. So you get maximum coherence. You open a freaking vortex. That's great. Anyway, I forgot that I had that slide here. Does it have to be water? No. But water is great. I don't think plasma breaks coherence. That's what ChatGPT thought that day, and I disagreed with it, but I didn't catch that was still on the slide. Anyway, final summary, alien physics level. If TUFT is correct, a spherical water shell plus EM U1 pumping plus cavitation collapse equals artificially induced topological torsion burst. That torsion burst exceeds the geometric threshold, flips the S1 fiber, and yields a temporary wormhole throat. This is low energy, high precision engineering. Aliens would pick this method because it's stable, it's cheap, it requires no exotic matter, and it scales to ship-size shells. And I haven't read this book, but I liked it. I liked these images. I don't know if I think that's a real photo, but I don't know if it's a UFO, but it looked cool. And anyway, so Catalina's hidden visitors, you know, all this stuff. But anyway, there's stuff going on at Catalina. This models what's going on. Maybe aliens are coming. This is what they're doing. I don't know, but you know, it might be. I hope this has helped elucidate a mystery. Now, this is kind of my sci-fi day. I don't know for a fact that aliens are doing this, but you know, it's a good theory. A hypothesis. Actually, this is a theory. It's a hypothesis. They're using my theory. Now, I want to go on to my other set of slides here. Very bad men. No. It's alien. I don't really think there might be men in the future doing this stuff. Some of the grays might be people in the future.
Oh, Jenny, I'm sorry. Did I mess you up? I took down I took down your
No,
slide deck and
you
I put up the
didn't
paper.
mess me up at all. I was talking to someone in the comments. I was laughing.
Do you
I was
want me to
actually
put
go
your?
to the next. This quantum coherence is self-interference in time.
Oh, okay.
Yeah.
This one. This
Yeah.
one. Okay. I'm
Yeah.
terribly sorry. I'm
Oh
terribly sorry.
no!
about
I was
that.
going to go to this next one. You just had it up, then you took it down. You're not. Don't be sorry. Yeah, perfect. Thank you, Tim. Okay, so this is what I've been doing over the past week when I should have been working on the Barger thing, but I've been working on this instead. So this is quantum coherence's self-interference in time. It's a paper, not slides. I've suspected for a long time and often said that you could combine the Bell inequality and the Leggett-Garg inequality and create a new inequality that combines them to show. Thank you. I'm looking at the comments. Someone says I'm great. Thank you. I think you're great too. I like water too, Archon. I should avoid the comments because I get too caught up. But anyway, you can combine these inequalities to get one inequality that deals with both space and time at once. I have an untraditional appreciation for Leggett-Garg. I think that Leggett-Garg is basically coherence in time as well as space. And I think that Leggett-Garg is sort of about the question, is the moon there when you're not looking at it? And that was kind of Einstein's whole problem with quantum mechanics. Like, why is it not in one particular location? Well, it's because it's non-local. And that was the issue with quantum mechanics, is that quantum states are sort of everywhere and they're sort of all the time, and they don't have an exact location in time or space. And I think Leggett-Garg is getting to the heart of that. That's why there's no independence of measurements in Leggett-Garg in time when you look at it. If you look at the Emery-Clark, I think it's Emery-Clark. I've read that paper so many times. I think I have that right. And if you look at the Emery-Clark summary of the Leggett-Garg, one of the things, the assumptions, is that things are independent in time. And I think that's the core of Leggett-Garg. Anyway, then there's Bell, and Bell is about spatial locality of separated quantum states. But I think that the core of quantum, and the core, we talk about entanglement, and that's of two separate quantum systems. But the thing about entanglement is that you're getting into this thing where you have to consider two separate quantum systems. And you really don't. Just one quantum system on its own is everywhere, all the time, interacting with every freaking quantum system everywhere. And they don't have to be entangled. They're already like that. Every quantum system is entangled with every other quantum system. And that's kind of an intense thing to say. And it's true that these quantum systems are more entangled than others, the ones that you pre-entangle and you set up and everything. But at some level, every quantum system is everywhere. And you can particularly entangle certain ones with others so that it's a primary effect. But at some level, every quantum system is everywhere at once, entangled with every other quantum system. And I stand by that because they don't have an exact location. Yeah. Yes, Nano. And anyway, I kind of started getting into this. I got into this young because I was just obsessed with I just got obsessed with quantum entanglement very young, and I thought about this, but eventually I started resenting this whole entanglement talk because it's moving away from the real core, which is that a quantum system on its own, not worrying about other quantum systems, is on its own non-local. You don't have to involve another one, and it's like lovely to talk about, once they're entangled, once they're linked, they're in love forever. You can get all romantic, Romeo and Juliet, but you don't have to do that. Like, just the one thing is everywhere. Like, you can go Advaita or very you can go the other non-local way, non-dual way. One, I am one, and so you don't have to do the romantic way. You can be the Buddhist on the hill way too. So anyway, I'm just trying to explain that you don't have to be romantic about entanglement, but I like the romantic view. But it's important to remember there is a non-romantic way of thinking about it too. That it's like just the one thing on its own is everywhere. So anyway, but that's just a complaint. This entanglement stuff gets too romantic. But anyway, interference in time from the Schrodinger equation. The Schrodinger equation generates unitary time evolution. The expectation values have these cross terms, which involve a factor of IT or IDDT. And anyway, I times T just means imaginary time. Imaginary time allows for interference in time. What does interference in time mean? Well, basically that means that things are interacting with each other across time in the quantum waveform. Now, that doesn't mean that classical things are interfering in time. That would be pretty odd. Like, I can't talk to myself last week, but it's possible that waves in my brain can access things that my waves last week, which is weird to think about, but if there is a quantum wave in my brain, that's possible. And it could be that there's waves in my brain that can access stuff that's in next week too, which is weird, but possible. And that's not classical signaling because it's not a signal being shared. It's not a code. I can't get my words from next week. I can't know what happens next week, but I might have something coherent in my waveform that's going on across all times, which is weird to think about. But there's something that has to be consistent in my quantum waves, assuming there's quantum stuff in my brain, but there probably is. There almost certainly is. There's something quantum in there. I mean, we have quantum stuff in here, right? So there's a quantum wave, whatever. The quantum stuff in my brain has to be consistent across all space and time. It's weird, but it just is true. It's self-consistent across time because it interferes with itself across time. So if you're a quantum guy hanging out, if I was in a quantum coherent state, if I'm this Buddhist master and I've managed to get my entire body quantum coherent, I don't know if that's possible, but let's pretend it is for a moment. I'm a quantum coherent Buddhist monk. I can see my whole past. I can see my whole future, all the possible futures, all the possible pasts. It's all open to me. And I'm there. That's quantum coherence. So it's all open. And that's a little bit weird. But I can see it all. And also I'm communing with all of it, and I can change all of it from here all at once, which sounds sort of like what they talk about with Padre Pio, bilocating and all this stuff. And now it's like, do you believe that? And it's like, I don't know. I'm open-minded. The faith is open-mindedness as far as I'm concerned. I can't say I believe that Padre Pio could bilocate, but I'm open-minded. It's possible. Okay, now, we introduce a new inequality, this thing. And anyway, this thing is, if you're quantum, this thing is obeyed. And that means that quantum things are non-local in time as well as space. So anyway, I'm glad I said this because it's been waiting to be said for so long. And my dissertation needs this, and a lot of things need this. I need to put this into my long thing, my many long things. So things are non-local in time as well as space. And finally I said it and I proved it and I did it, and I'm happy because that's done. Because I've been arguing this based on Geissen's multi-simultaneity for a long time because it proves it, but it doesn't prove it in the way that this proves it, which is theory. Geissen's thing proves it through an experiment, and then you can back theory it. Yeah, isn't that cool? That's really cool. The zoo of particles under pairs on. That's great, Archon. Yeah, I'll check it out. So yeah, there's a lot of cool entangled experiments, and some of them are in time. So there's a lot of the multi-simultaneity violation experiment proves entanglement in time, and there's a lot of others that prove entanglement in time. But those are experimental proofs of entanglement in time, but there's never really been an inequality like Bell's that proved entanglement in time, and this is it. And I did it, and I'm happy. I'm happy that I wrote this down because now we have a theoretical proof that quantum particles violate causality internal to their system, not classical causality, but quantum causality. So then I talk about that a little bit in this paper, but then I do something a little bit backhanded and bizarre. I talk about how linked particles might have a backhanded way of talking to each other. So, you say, well, there's no way to send a signal between them, so that's okay. No problem. There's no FTL. And Jack is like, I think there's a way to get FTL. And everyone's like, no, Jack, there's no way to get FTL. And I should talk to Jack about this because Jack's been looking for a way to get FTL for a long time. And maybe Jack's done something like this. I'm not sure. But anyway, I think I kind of found pseudo FTL. And that's not how I presented it in this paper. But I think I have a kind of pseudo FTL. This is, and it's not FTL. This takes time. If you sort of slowly decohere a large set of, so you have this kind of blob of entangled particles here. Hey, Jack. There's this blob of entangled particles over here, and they're all kind of entangled with each other. So I hope that we have this mega blob. It would be nice to have a molecule here and a molecule there, or a blob of molecules. It's still hard to get entangled molecules or blobs of molecules, but let's say we have them. And you mess with them, and they do something. And they do something when you when you poke at them. You can kind of create a seed crystal into these other things that they connect with. Anyway, okay, so you have these entangled things in this classical format, and every time you unentangle one by poking it, it does something to the thing around it. Because it's entangled with the other thing, the set of things it can do to the classical shit around it is limited by the fact that these things are entangled a certain way. So basically, you can imagine, you can model it as telepathy. So I'm entangled to my friend Jack, and me are entangled. Okay, let's just joke. And I'm thinking cheese. And I said, I'm trying to tell Jack, cheese, cheese, cheese. Anyway, and so I'm thinking cheese. And so Jack's getting this message, and it's like yellow, yellow. And I'm thinking Swiss cheese, you know. And Jack's thinking yellow, whatever. But anyway, I'm trying to send the message Swiss cheese, Swiss cheese. Anyway, but so anyway, every time he disentangles one of his particles, he might get holes, or he might get this. So you're slowly making the ideas of his brain generate certain patterns, like a seed crystal that's sort of slowly evolving patterns as you disentangle the entanglement between the two brains, is the idea. And so but of course Jack and I would have to be entangled somehow, but you can assume that most friends are sort of entangled, right? Because you've talked long enough that you sort of get some sort of entanglement going. I don't know. That might not be true, but you can just imagine. So anyway, the idea here is, though, that if you have two entangled things and you disentangle them slowly, you generate seed crystals in the classical matter around it. And even though you're not sending a signal classically, you slowly, but not very slowly, like kind of over a period of a few seconds, you can generate similar words in the classical system around it. The thing is, you're not going to be able to predetermine the message, which is the weird thing. So you have to just sort of be in a certain state, and you just want to share the state, and the state that will be shared will be determined by what state you're in, which is weird because, like, when you communicate, usually it's like, well, I'm going to tell my friend we're going to buy Swiss cheese, but it's like, well, you're in the Swiss cheese wanting state, and then you just decide, you realize that, and they're going to realize it at the same time. So that would be how a sort of telepathy would work. If there is telepathy, it wouldn't be something that you oh my God, you guys. But like, it's not something that you decide ahead of time. Oh my God, you guys, your conversation over here is getting very, very, very odd. But this is what you would expect in these kinds of places. But anyway, so yeah, my point is that there is a possibility that you could send messages, but they're not predetermined messages. They are quantum state-based messages. And as we know, quantum states are somewhat random. But you could use this to send similar classical states at two sides of a divide, and get the same message on both sides. You can decide what the message is going to be, but you would know once you get this that they're getting that at the same time. You might not be able to check to verify, at least if they're in Andromeda, you wouldn't be able to check. But if you know that you're entangled with someone in Andromeda, once you know that, now you'd have to classically gone to Andromeda to set this up, which just makes it kind of useless. But the point is, if you know you're entangled with a friend somewhere and you get this, you'll know that they have that too, because you have it. Anyway, I don't know if it's very useful, but the point is that this kind of entanglement where you both get something classical that's similar is possible. It's not the same thing as sending a code. It's not quite the same thing as FTL communication. So I call it communion because you're both getting something at the same time together. So it's something. Yeah, and it's also, you could be communing with your brain or someone else's brain in a different time if you're entangled with them, but you have to verify you're entangled. And how do you do that? How do you verify entanglement? It's kind of complicated. So like when I talk about these things, I'm being very speculative. I'm not saying that we've proven that telepathy is possible. I'm just saying, assuming that you're entangled with another brain, that you could do this, but entangled. But if you have two entangled states that are large enough that you can keep getting measurements, or even if you just have, you can impact on the classical world around these states. You can impact on the classical world around these states to get something out of the quantum world into the classical world, where both sides of the classical world are impacted by the quantum state. I don't know if I'm saying this pretty effectively. I'm saying that you can get a classical shared state from the quantum shared state. You can't send a code, but you can get a shared classical state out of the shared quantum state. I hope this makes sense. Anyway, I think that was the point of my communication today. Take it away, Tim, and I'll be happy to do questions and answers. I know I kind of rushed through everything today.
Jenny, that was awesome. That was awesome. That was like total stream of consciousness. So, okay, let me bring everybody back in. I'll take your paper out. Yeah, I don't know if you saw me in private chat. I was like, you're hitting it. Keep going. And wait, good sound. Oh, look at that. Nathan and little Nathan. That's perfect for Christmas time, man. So guys, before anything else, let's put our hands together and give Jenny an enormous applause. Jennifer Nielsen with kind of you expanded on it, and actually you put a lot more energy, and I think you covered a lot more ground, and what it connected to was so much better. I am so pleased that you were able to talk about that. And then you referenced quantum communications, you referenced like ship-sized wormholes. So you went into all of these really amazing classic science fiction ideas made real, right? So I love it. Thank you so much.
I hope I was able to pile more ground. It would help that I wasn't having to move my phone around or trying to negotiate with the Faraday cage.
Mm-hmm.
And I've made more progress on some of my other ideas. So does anyone have any questions about the cavitation stuff? And Dan, did I describe what you were doing okay when I brought your stuff up?
My internet dropped out during that that section because I live under a rock basically. So that's just how it is here. The one thing I was going to say, I don't know if I mentioned this to you before when we were talking, in regards to, so if we're treating timelines as the S1 loops, and if we're treating particles and stuff as, say, knots and twist within each individual given S1 fiber, that would, and we can get deeper into this later, but that would naturally kind of lead to like an interference pattern in time that you could pick up too. So
that kind of makes sense.
Yeah. So like look into that, and you'll probably find something there.
That's interesting. Can you say this again?
So if you have the timelines are S1 fibers, right?
Mm-hmm.
And we're just approximating them to a fiber because it's going to be some sort of weird twisty sorty knot thing that might have like a quasi recurring pattern in the twister and the knots or whatever. And I'm digressing. The knots within that S1 fiber. So say you're picturing a string of loop or like string.
Yeah.
Tie a bunch of loops into it, and then reconnect it so it's still for the most part still getting that same curve. Now say you have an observer here. As you rotate it, the S1 fiber through the observation point, the ripples on the knots in the rope will manifest as like an interference pattern in time.
That makes sense. Yeah, that makes sense. An interference, but how would you measure that?
They have recently measured an interference pattern in time.
Okay, who?
using something to do with like photons. And I'll send you stuff about the
Yeah,
experiment.
that's interesting. Yeah, I agree with you that there would be an interference pattern. I'm just not sure how they would measure it, but it makes sense there would be.
Yeah, I can get back to you on that on the papers.
Yeah. Cool. Yeah, and then the Everett. Do you want to talk about the Everett thing?
And which in like at what level?
Just the basics. So you're trying to take a line element and connect it.
Yeah, on what we're so basically like so as a series of people have shown that general relativity is emergent from austere quantum systems that have no collapse, in which case any system within general relativity can be seen as a semi-classical approximation of some entanglement entropy. So there should be a way to make a minimal extension of general relativity to map these continuous non-collapse branches, because it's that discontinuous thing that from the collapse mechanism that really throws in all the issues of quantization, and that's a whole different conversation. But there should be ways where it'll help with navigating these things at seemingly FTL speeds, because there's pathologies that come in where basically you can't have FTL travel existing in a universe that doesn't have multiple timelines. It doesn't support it. And then there are people who've gone into that very rigorously. I think the one who's gone the deepest on it is Dr. Barak Shoshani from Brock University, but he builds on the work of David Deutsch and stuff. So there's a body of evidence here that says at least we should look into how to map out time more accurately, and that's kind of what we're trying to do.
Mm-hmm. Yeah, it's cool. Yeah, so I've been having fun talking to Dan about this project.
Is that related, by the way, to the whole idea with Aronov and the idea of like the quantum wave function evolving from both future and past and meeting in what we call present to kind of describe the whole collapse of the wave function idea?
Yep, and it wouldn't be collapse anymore. It would be effectively like you're getting the illusion of decoherence from the interference patterns that it produces, I guess would probably be a good way to describe it.
I have a slightly different question, not on the time topic, but Jenny, so in your talk, thank you, by the way, for everything you shared. And I just watched The Age of Disclosure, so that was really cool that I could then, track a little bit with what you were talking about. And so were you, in a sense, explaining how the spacecraft is able to go from space to air to water and just basically navigate all of that? I thought, and this is just my naivete, I'm not really super knowledgeable on warp drives and space-time bubbles, but the impression I got, at least from the documentary, was that space-time bubble that the spacecraft exists in is able to navigate into all those various media because simply there's no direct interaction of the spacecraft with the medium. It's the medium, whether it's air or water or whatever, is wrapped around the spacecraft.
Oh, I see what you're saying. Well, what I was trying to show with the water thing wasn't so much about how it avoids water or whatever. I was trying to show why it prefers water.
Oh.
Yeah.
I didn't catch that. Why? Yeah. Forgive me. Why does it prefer water?
Because water is a fuel that it's using to generate the warp drive.
Oh, so like when it took a dive, it was basically like a pit stop at a gas station?
Yeah, exactly. It's using water as its matter, that it's a preferred form of matter to pair with the space-time torsion, to vibrate and pair with the space-time torsion to link the torsion to the ship, to kick up torsion and change space-time local to around the ship, and then to move the ship relative in space-time and use and generate wormholes and a Cuvier style drives.
And you're talking about torsion in the context of like Einstein-Cartan type torsion?
Similar, not quite identical. I have a unique unified theory. It's a complete unified theory, which is unusual, and I realize it's a very bold claim, but it's the first theory that generates all of the masses uniquely and from first principles. All the particle masses we have so far, I've unified the forces into one field, and so my paper is also in peer review. So it's a unique, weird thing, and I realize it's going to be very controversial. I'm going to be a very stand-up, breakout, weird maverick, just for saying this. But it's in peer review because it was well prepared and rigorous. So it's very similar. It reduces to Einstein-Cartan. However, I have propagating torsion, and Einstein-Cartan does not.
That's interesting you say that, because I have been looking into that topic quite a bit, and I understand generally, like with the Einstein-Cartan, torsion is not propagating, and the reason it comes up is because I did mention I work with Raymond Chow, and he's very interested in gravitational waves, and as we know, the Einstein constant kappa being so small is usually the deal breaker with any kind of actual gravitational physics that you could do in a lab for gravitational waves and such. So, and I was looking at the topic of torsion, and I know that Einstein-Cartan is not propagating, but there have been other, like a Poincare formalism of some kind, if I'm remembering correctly. And then there's the whole, what is it, metric affine gravity, that's even more general, that involves torsion and non-metricity and contortion, and quite frankly, a bunch of stuff that I sincerely don't know. But so I thought maybe when you were saying that you were working with a very general framework, I thought maybe you were talking about MAG, like the all connections.
I'm working with with torsion from the Hopf vibration, twists in the Hopf vibration.
Okay.
Yeah. So it's if you look up topological unified field theory on the complex Hopf vibration, that's me. I'll post a link here in the general comments.
That would be great. Thank you.
There, I just posted it in the general comments.
I do have one question for you, Jenny, if you have the time, and I know it might be a little bit of a long-winded thing. Do you have any comment on like the relationship of like fiber twists and like Bianchi identity, or
to the Bianchi identity?
Yeah, I think I'm drawing a blank on that.
Well, I'm actually looking into that. Jack's been talking a lot about the Bianchi identity, and I haven't on it. And there's also connections to Emmy Noether's work, and I'm just breaking into that. So I'll be looking into that soon.
Because I think, if I'm not wrong, some of Heim's stuff predicted something similar.
Yeah. I think that, well, people are telling me that my work on Heim's have some parallels.
I mean, he gets some things wrong, and that's, me and Joel have discussed that, but I do think there's something there.
Okay, interesting. Yeah, and I love collaborative talking and shooting the crap. So like, this is a lot of fun for me. If you want to keep going for a bit, I have time.
Yeah, Jenny, I'm totally down with it. Yeah, next up is Curtis. In fact, I have to text Curtis. Curtis, where are you, buddy?
Yeah, so the connection to Heim's theory became quite clear in your talks, and we have to connect on it a little bit more. So it's not. So while both are using some of the same ideas and put geometry first, it's a very different framework. So
I'll say this: it seems like, and me and Joel have had conversations back and forth on this. It seems like my interpretation of time fixes the issues that arise out of Heim theory, because he tries to do a standard 6 or plus minus metric instead of what we're doing, and that seems to change some of the
I use a Euclidean metric mostly. What do you think of Euclidean metrics, Dan?
What, like, in what respect?
Euclidean metrics don't have the standard metric. Do they work with Heim?
That'd be a question for Joel.
Okay, Joel, what do you think? Would Heim work better with a Euclidean metric?
Like I said, I don't think that you can directly translate both theories into each other, because there are some Heim goes beyond, because he also tries to explain consciousness completely within the framework and stuff. So I think again, Heim's theory is a little bit overkill, and you might just explain a subset of the questions, which is tried to be completely in this framework, which is still way more than quantum mechanics and general relativity do on their own. So so what you're doing is very interesting. If it holds true, it's great. And I have to correct you actually at one point. So Heim's theory is maybe the first to claim to derive the particle masses from first principles.
Okay.
So you have three inputs and geometry, and he derived particle masses.
Interesting. Which did he get the neutrinos?
Yes.
Interesting. See, I've never seen this.
There was even an excited state where the Higgs boson was found. So
interesting. Okay. Well, that's good to know.
That was calculated 1982 in Hamburg on the DESI synchrotron supercomputer that they had there by experimental. It was never translated, right? So it's only exists
I
in
never heard of this guy.
It's there's no real English publications, and because
if you send me the German, theory, I could handle the German. I don't speak German, but I could deal with it.
ChatGPT might be a big help here, and I will send you the source material, and also if you have Discord, I posted the invitation link to the Heim theory Discord in the private chat here. All the material, and there's also, we have a whole group working around it, and there's also modern papers which are in English, but they are not to the full extent of the Heim theory framework, just parts of it.
That's very cool. Okay, well, thank you. I have a proposition for consciousness, but I haven't published it because I think that consciousness falls somewhat into philosophy, not physics, if that makes sense.
Yeah.
So it's like, what do I do? What do I do with this? I also think that it's a little speculative right now.
Well, Jenny, I have a suggestion. If you have stuff like that, I mean, we don't do consciousness on APEC, but my thought would be it's okay to have a crossover. Why not publish it? Why not? I mean, you could do like a, if nothing else, do like a paper on it.
I think I've been intentionally holding back because I want to be established as, like, in the physics field, if you start talking about consciousness, people think you're weird. And now I am weird.
No, that's not true. Consciousness is the end road for all science. The only thing is, I think that you're like 50 years too young to be writing about consciousness. Usually you get to a certain age,
That's true. Or you're a philosopher of mind, and then they don't mind.
You're ahead of your time. That's all. You're ahead of your time.
Well, thank you.
Is talking about aliens any less weird? I'm not quite sure about that part, but
I think that I've just given myself permission to talk about aliens and telepathy and weird things, and just let people think that I'm eccentric. But if I talk about consciousness, they're like, no, Jenny, you can't talk about consciousness.
I've been working on consciousness myself only because it sort of fell in my lap with a couple colleagues, Ahmed Farag Ali, who's a very established physicist, and then Ruben Laukkanen, who's he does a lot of research in neuroscience. He's at Oxford, and we have been looking at the role of superconductivity and SU3 symmetry and the connections between symmetry and consciousness. And if we ever have a spin-off from APEC that involves consciousness discussions, I would be all for it.
We could do a consciousness day. I lied. I did one paper with Jack about biological fields, and it's basically consciousness.
if I mean, speaking seriously for a moment, this has just been my experience from what I've read, but most of the great physicists out there have explored consciousness in one way or another, right? And then in our community, whether or not folks talk about it or they silo what they focus on, what I found is there's incredible overlap, right? Propulsion, energy, extraterrestrials, consciousness, and maybe people don't connect them, but they at least seem to have an interest in all of these areas, right? It's just frontier science.
And one thing I found sad when I was an undergrad was that, well, a lot of people were scared because Brian Josephson made an offhand comment about telepathy that went on a set of postage stamps, and he got banned from a set of amazing conferences because he made those comments. And it's like, what? So people got scared and no longer made these offhand kinds of comments, especially not in publications. And like, I know people who believe things that are pretty wild and out there, and they say them in structured, rigorous ways. And they're like, well, don't tell anyone about this until after my death and things like that. And it's like, what? Like, do we have to be this cowardly?
Hey, Tim.
Mhm.
I hate to channel Jared, but what does any of this have to do with propulsion?
Well, we are off the rails a little bit. It is
You
2:30,
wait, Tim, you left the rails an hour and a half ago.
we're missing one of our presenters today, and so Jenny graciously filled in for us, and so Curtis will be here in about half an hour.
It has to do with propulsion, though.
Yeah.
Here's a suggestion. We don't know. Okay, if we believe in EATs, we know that ETs connect with the ship in a unique way. We don't know how they control the ship. There were no control factors for how the aliens connected to the ship in the Roswell. That's one reason we thought, oh, well, the air balloon thing maybe was a thing, because there was no control panel or what hand. So one possible solution to this, if it is a ship, was that they're controlling it with their mind.
Yeah.
So then we have to get into QFT. Then we have to say the brain must have some kind of quantum field in it. And then we have to say there has to be a way of hooking the brain to the ship. And then, I mean, this is getting pretty sci-fi, and it's not directly propulsion, but...
No, Jenny, so actually, in terms of propulsion, what are your thoughts on ER equals EPR? Because you were talking about wormholes, right? You were talking about various ways to do that. And for me, that is an area that's really interesting, because it's almost like a way around this challenge of you can't go faster than the speed of light. And then what intrigued me in your talk was you were discussing this idea of making ship-sized wormholes without negative energy. And that, again, I'm connecting that to ER equals EPR and saying, okay, maybe that is how they're doing it.
Yeah, in my work, what I don't think that ER is exactly EPR. It's not, but they occur in the same connection space in my work. So there is a space where everything is connected at once in a certain sense in my work.
Okay.
Yeah, it's hard to say exactly what I'm saying, but there's basically there's spaces in between. There's this in between sort of space where everything is connected like a bridge.
Okay.
Every point is connected to every other point.
So I got two things that are kind of nagging at my mind. I'd be really curious to see what Jenny's theory has to say about electrostatic propulsion, and if there's any gravitational connection there. I think that would end up lending really well to possibly explaining or not some of the experiments that some of the people do here. The other thing, in terms of like, how does the consciousness thing connect to like propulsion? It's
so weird, like
we have to be careful on like how we word this, because it gets into like people assuming woo really quick.
Yeah.
There are ways that you can have no control panels in a propulsion, in a vehicle,
Mhm.
and it's reading off of your brainwaves, but it's entirely non-invasive, and it's not
Mhm.
using any quantum magical woo. It's
That's
using
what I
sensors
was
that already
exactly.
exist. I mean,
Exactly.
this is something that people have done for video games right now. Is they train an AI to read the brainwaves, and then they use it for like minimal latency on controlling video games. And so if you can make a mapping between those connections, like it's not a very far jump between mapping to a video game control versus a fly-by-wire control, for
You
example.
got it. You got it. That's what I was. Yes. And the thing, and yeah, exactly. And so, but I guess.
Oh, I'm sorry. I don't
No,
want
I'm
to
sorry,
interrupt the
Tim.
train
I
of
didn't want to. I think you had the thought, the ground.
Well, I was also in terms of B-field Brown, and this goes to, I think, to what Drew was saying. Drew is looking for physical, hands-on, engineerable ways to approach this problem, right? Does your modeling point any direction or roads, I guess, there?
Where, Tim?
Just in terms of like actual physical solutions, engineerable stuff that people could take and build or potentially improve what they're already building, or
Yeah, I
things
think
like
it
that.
does. It should, and it does. I need to actually I need to talk to people about what they're doing and think about it in more depth. But yeah, it should have exact applications.
I mean,
yes.
if you're, and I'm still going through your paper. I'm on like page 78 of it now. But if you actually can accurately go through and rederive particle spectrums and field strengths and all that stuff that comes with it, there should be a way that you should be able to basically back derive anybody's work here and
Yes.
explain it through the
Yes.
lens that you have the right data sets too. And whether or not people are going to be willing to give those up and work with you on that, that's something you'll have to work out with them. But
exactly.
I think that's how you can make a connection between some of this theory stuff and some of this engineering stuff.
Yeah. If I know what people are actually that's exactly the thing. If I know what people are doing and I know the data they have, I can take my data, not my data, my theory, and explain what they're doing. It should be a universal kit.
How does that help us, that the guys that are making the data? We already have the data. Whether your theory works or not, we're going to continue doing what we're doing.
I'm not trying to tell you not to do what you're doing.
So Drew, what they can do here is they can
together, but they're not of any value.
The thoughts that have the value is we could time travel, Drew, and you can't yet.
That's
you might be able to time travel.
That's not helping.
Thrust, and you don't even talk about it.
No, so what?
Time travel? We don't have an APEC time travel zone.
Yeah,
I think again these are kind of two worlds that have to meet in the middle, right?
We gotta
physics informs engineering, and the engineering provides feedback to physics.
Exactly.
And we have to crawl before we can run. Now, how something like this might be able to work is if you have an accurate enough theory that you can model some of these experiments with. Once you have enough starting input parameters that, it's like, say, for, anybody's XYZ experiment, you can go and you can make a simulation of it then based on, whoever person's physics. If, say, conventional physics doesn't explain it, and so we need something like Jenny's do, you can take her framework, plug it into, take X person's framework and plug it into Y person's data. And then you can make a simulation for that, and then from there you can start going through stochastic simulations, and you can narrow out, what's the most optimized, what's the worst, where the current set exists in that, and then what you might be able to do to, iteratively make better versions, because you might be able to find something in the math that the computer hit up that your human brain might not have.
And without builders, what is theory?
Well,
useless.
A good example of this really is the Manhattan Project. That's one of the few examples we have of, how do we go from all these theoretical numbers on papers that don't make any sense to some engineers to making an functional, actual, usable piece of engineering equipment. Right. That was a case that went from the paper to the engineering. Usually, it goes from engineering to paper. Mm-hmm. We need to start applying that model more.
Mm-hmm.
Can I ask a question along those lines, by the way? Because I know you, if I can take us back for a moment just to the torsion topic, because if I understood right, that's an important part of your work. Is that right?
Yes, that's true.
So one thing I've been very curious about, and I've tried my best to try to identify, is we know that in general relativity, there's the Newtonian limit that allows us to nail down the coupling constant kappa, the usual 8 pi g over c to the fourth.
Yeah.
Whereas with torsion, though, as far as I understand, there's never been any observation or experiment done to actually measure and identify the existence of torsion. So it makes me wonder.
The Barger experiment is it.
The which?
The Barger experiment I just documented is not known, but is it? It is it. This is the torsion.
So would that be almost like an analog to the Newtonian limit of the torsion field equation?
That's what I have. Not the experiment doesn't give us that. My theory gives us that. Okay,
so for instance, what is the coupling? I mean, let me start with this. So if I understand, vanilla flavored Einstein Cartan, you've got basically you assume the same coupling constant for both the curvature and the torsion. But if I understand right, you can split those off if you allow that in a Lagrangian. You can split off those terms and allow them to each have their own coupling constant. Is that right?
Yeah, that's right.
So in that sense, if I understand right, there's no like Newtonian limit in the sense that we know obviously, bringing it back to actual grounded experiments. Obviously, we have like the Cavendish experiment.
Oh, I think I understand what you're saying. Like the Newtonian limit of what you can get.
Yeah, exactly. So exactly. So like I think individuals like Drew who are like heavily on the experimental side, they like to see that there's an actual concrete, like workable experiment that they can measure, like a Cavendish experiment in the lab, right?
The Barger experiment would show what the acoustic limit is. But I described the EM limit in the same paper, but that would also lead to a warp drive. The EM would also allow warp drive.
So it sounds like it's a very, I mean, for lack of a better term, as we always call exotic physics. So it sounds like it's an exotic phenomenon that would occur. And it almost seems like it's an all or nothing. Like you get something really extreme out of it or nothing. There's no kind of like mundane experiment like Cavendish, if you will, that would allow you to...
There is a mundane version. The mundane version is the classical Barger snow globe, and if Mark was here, he could talk about that.
Is it like a
so basically you're saying like the laboratory test you would do for that is you're manipulating sonoluminescence, basically.
You're doing what now?
It's really
is that what you're saying?
Sonoluminescence might be an aspect of it. Barger wasn't really interested in sonoluminescence so much as cavitation.
Well, sonoluminescence comes from it's a byproduct of cavitation.
That's a byproduct of cavitation, But he was less interested in the brightness as in the
spin, right? Like it sounds like you guys are talking about maybe a more extended model that includes electromagnetism and etc. I'm just thinking about the most basic torsion.
The most basic one would be the cavitation experiment with Barger. Hold on. Let me link to this paper. That seems like a thing that I could do really quick. He doesn't describe it as torsion, unfortunately, but I could rewrite this paper of Barger's and describe it with torsion. Would that be helpful? Would you guys like that?
Oh, I mean, I would be all for it because, like I said, in my group, we look a lot at propagating gravitational waves, and so since, as I explained earlier, since curvature seems kind of hopeless in the sense, because the Einstein constant is so tiny, there's been some hope that maybe torsion would be different in that respect. But then I always bring up the point, well, wait a minute, we're sort of building a house of cards because we're trying to do gravitational wave physics in the lab and it's already speculative. Now, if we bring in torsion, which has never been observed at all in any kind of experiment, even a Cavendish-like experiment, then we're just adding conjecture to conjecture in a sense.
So my talk, the core of my talk was that there is this test, the Barger cavitation test in 1964, a very basic down-to-earth test of vibrating water in a sphere. That thing is a way to demonstrate torsion in the lab, and it did it in 1964. That was my point. I don't know if I said it very well.
I did not catch that. That would be major for me. So what was the coupling constant that came out?
The coupling constant? I didn't look for that because I just showed that it matches what I did in my paper.
That would be huge because, as far as I'm aware,
it matched my paper. All I did was I checked and I showed that the thing that happened in the experiment matched my paper. So I wasn't looking for a coupling constant. I looked and I compared it to the predictions of what my paper predicted would happen.
And I mean, if it's go ahead.
So I looked at what
correct me if I'm wrong. The premise of how you're saying that this connects here is that this experiment that was done back in the 60s has gone. The theory explaining it has gone unexplained for the last 60 years until you were okay. Yep.
Yeah. No one has known why it did this. Nobody had any clue for this long. And I myself ran many simulations with everything I could think of, and other people have done the same thing. And I came up with things that I don't think other people have even checked. I checked cymatics and things like that, everything, and nothing worked. But
well, I guess what I'm saying is say, for instance, take the Cavendish experiment as an example. So we know obviously there's a torsion balance and there's it's a very straightforward analysis. Mm-hmm. And from that you can determine what G is, right? So is the experiment you're talking about equivalent to that in the sense that by just simply observing some sort of, I'm assuming, torsion related motion, you could then essentially just use
I get it. I get what you're saying. I think it's not straightforward as that because it's a geometric phenomenon. And if that makes sense, torsion is related to fiber spacing.
Are you talking about in your theory or in plain old Einstein-Cartan where it's basically spin coupling?
It's not spin coupling in my theory, and it doesn't obey Einstein-Cartan. Yeah.
I see. What about a Bohr shift in the gravitational waves?
Yeah, this theory does not obey the output that we observed in Barger is not Einstein-Cartan. It matches my theory.
Oh, yeah. I see. Okay.
Which is geometric, and so it obeys fiber twist holonomy.
But it sounded like you said you could reframe that paper or that work.
It's not matter spin. You can't reduce it to spin and matter.
Oh, I see.
Yeah, okay. It's something going on in space-time itself, which is, and I might be able to find a coupling to a way to think about matter coupling, but it's not the spin in this sense.
It's almost like trying to think of the Ball-Marinoff effect without QED.
Yeah, it's like that. So what I
guess I'm thrown off because you mentioned torsion repeatedly in your discussion, so I can't help but wonder. Dan was making the point that any elaborate theory should reduce to the more basic theories that we already know. So if you reduce your theory to Einstein-Cartan in the appropriate limit, does it still reproduce the results of that experiment?
I think I'm not sure because I haven't tried it. The thing is, Einstein-Cartan doesn't have propagating torsion. And this might involve propagating. I believe this involves propagating torsion.
Gotcha.
Yeah. Gotcha. So that's the problem is it depends on what
the obvious question. What does propagating torsion have to do with anything? I don't even know what it is.
It involves
that in the way that it's going to make a piece of paper fly.
Yeah, it could. But I understand why you're asking it because it sounds impractical. So I'm trying to reduce it to a way of talking about it.
It sounds absurd. Is the reason I'm mentioning it.
Okay. Well, I think what Drew is saying is we need to come up with a way to make this highly theoretical stuff sound applicable, and I think that we need to come up with a way to make the community.
Yeah, I think there's a way actually, if I understand correctly, but please correct me if I'm wrong. You could think of, so Drew, as you probably know, gravitational waves have been measured by LIGO in an interferometer type configuration where there's stretching and squeezing of basically the tunnels, and then they observe it that way, right? So if you have a torsion wave come in, rather than an interferometer that you would use to observe its existence, you would use something that has spin, like maybe I'm picturing like a gyroscope, and the gyroscope, I believe, would precess in the presence of that torsion wave. And then if you prove that that torsion wave exists because of that precession, now in principle, you could continue doing all the things that you do with gravitational waves, but it would be with torsion waves. So it'd be like another type of wave propagation that we haven't seen in nature before. I don't know if that helps.
But I'm not building a gravitational wave flying saucer today or tomorrow or within the next 1,000 years at this rate. And I know I'm not going to build nothing with no torsion wave thing. So again, how does this relate to the real universe?
Well,
the thing
Mark
we actually live in.
Well, Mark is trying to build a spin torsion device. So that's like torsion. Do you know torque? Torque and torsion are related.
Yeah, I actually have a master's in aerospace engineering. I know a little bit about torque.
Okay. So that's my point. So my point is that torque and torsion are similar ideas.
Maybe what Drew is getting at is how does this help us with propulsion, perhaps specifically? And that I personally admit, I don't think gravitational waves or torsion waves are likely to play a direct role in that sense. I mean, the talk I just gave attempted to make a connection there.
Well, Alcubierre drives. In my theory, torsion is involved in creating an Alcubierre style drive. So that's how. But I guess if you want traditional propulsion without a warp drive, then you're not going to want. But if you want a warp drive, it's useful in my theory.
That makes sense.
Yeah.
So if we could magically generate these things, they could somehow become a warp drive.
But it's not magical. In my theory, this is approachable. It's actually approachable because it doesn't take much energy. So I'm trying to say that maybe if people like you were willing to try to test my theory, it's possible we might be able to have warp drive in the next 10 years. That's where I'm thinking. And I might be crazy, ambitious, optimistic.
Yeah, no, and I think it's just I think all of us need to work on it's cross-cultural communication, right? Versus theoretical and hands-on, and these are different. They're different traditions and they're different communities, and so you're not necessarily speaking the same language, and it's just bridging that gap. But I mean, that's one of my big hopes for this conference is.
The way that I understand Jenny's warp drive, and we disagree about this, and so I'm sure we'll get into it. When you look at her actual metric, it's basically an FLWR metric. So I get what she's saying about her snow globe analogy. Basically, Drew, how you would test this is you do a cavitation experiment where you have this sphere of water, and then
I actually don't use a metric in my version, but yeah.
You had a metric in your one. Like I said, we were going to disagree about this, but in your one slide you did. And it was for Drew's analogy, in your snow globe of water, if you excite it in a certain way, you will get it to cause a cavitation bubble. When that cavitation bubble collapses, it forms plasma in a way that's not normally explained by the standard model, but is explained by Jenny's. Now, because it's spherical, normally it wouldn't make any impulse one way or another. It's just a cool party trick. Now, if you can tweak that to make it asymmetrical instead of spherical, it'll give an impulse one direction or another from the gravitational contribution of that plasma wave caused by the cavitation.
Why would we disagree?
We disagree about the plasmas before, and
I think
I get what you're saying. I get what you're saying. It's fine.
Yeah. Well, and guys, we're almost. In fact, I'll bring Curtis in here. We're almost at the top of the hour, and Curtis has a presentation that he's been working on for quite a while as well. So.
I need to get. I have things to do. Unfortunately, I'd like to.
No, Jenny, thank you so much. Thank you so much, guys. I'm overjoyed. We're having a total kick butt session today. This is really, really awesome. So,
and Drew, I want to thank you for your pushback. When I'm getting real highfalutin, I want to know when I'm not sounding practical. So,
yeah, I think it's just communication, right? It's like you spend all day working with numbers and abstract concepts, and and that's like where your brain is, and there's absolutely nothing wrong with that. It's just like, okay, now how do we over time?
Jason
how do we
just
marry
said is
this to the
interesting.
hands-on
Drew is
part?
making a perfected theory, a thrust without a perfected theory. That's interesting. I'd like to look at Drew's thrust and see if I can explain where his thrust is coming from. That might be interesting.
That's kind of what I was getting at earlier.
Yeah.
Did you say
Pretty much all you have
pushback
to
like
do is
inertia?
Look at Dr.
Like-
Wheeler's,
It's so fun.
go look at our patent. It fully lays out the entire physics.
Okay.
That and his insane third order perturbation stuff that nobody understands but him. But
Well, hey, I might understand it. Yeah, well, sometimes order of perturbations can be explained in a direct theory without the perturbations later. It's cool.
I'd be really interested to look at that, Drew, the perturbation stuff.
didn't Charlie give a talk on that?
I think he did.
Is there?
He did.
6 months ago?
He has graphs and stuff.
Does he have
in
a
it,
paper I
yes.
can look at or a slideshow?
No.
There's no slideshow I can.
Well, that's interesting. Bob Grainer,
he does
safe,
not.
energetic, PZT,
Well,
Magnetohydrodynamic.
actually, he does, but
That's interesting.
You're not
I like
getting
reading
it.
in the comments.
It's
Yeah.
not publicly available. But,
Well, no, you know what?
yeah.
No stress. I mean, we're, I think that we're making great progress today. I mean, again, amazing presentations. I'm absolutely overjoyed. So thank you guys so much.
Thank
So
you.
if it's okay, let's do this. Let's put our hands together one more time for Jenny, Lorraine, Nielsen. Jenny, thank you so much. Thank you so much.
Thank you, guys.
And
Thank you
guys,
so much.
thank you for your thoughts and questions and commentary for Jenny as well. Amazing dialogue, amazing presentations, amazing problem solving and identifying challenge areas, right? So let me do this. I'm going to take everybody out except for Curtis. Mr. Horn, unified field theory. I'm
Good
rubbing my
afternoon.
hands in anticipation. You've been working on this for a long time.
Yeah. Actually, it's been very
so
interesting.
you would ask me to give a link to Arnie as well, and I did. I sent that to him. So
Sure.
if he pops in, I'll let him in. I'm happy to. We have extra time today, so we can do a Q&A if you'd like.
Oh yeah, definitely.
Yeah, I think
We can have more.
Orestis, he emailed me back. He's saying it's just a time zone issue. So
Right. Yeah, no problem.
okay, so yeah, let me I will put your slideshow up and take it away, sir.
Okay,
And let me
sounds
know.
good.
I'm here in the background if you need me.
Okay. Yeah, sounds good. So I've been very busy working on this paper and secondarily this presentation. As you can see, I didn't put a nice background. I just did something very straightforward here. The main thing is I'm trying to get this paper polished up to at least the first draft, get on archive to have a record of it, and of course this presentation will also be a record of this work. Now, I definitely want to this work and acknowledge Jim Woodward's support. I did leave, I was working, and I went to join Jim and at the time Hal to work on this Mach effect thruster, and when you're doing physics, you do some experiment, you do some theory. It's always a mix, sometimes weighted in one way or the other. But, really, for those that aren't aware, the whole thing about inertia and understanding what it is, it's something that's not directly explained up until now in terms of having a theory that is fully covariant and meets modern standards, at least up until to Einstein standards, right, of general covariance. So that's something that we're going to address here. And being able to work with Jim was what allowed me to delve into the theory. Now, I do want to say that Jim really focused on experiment, right? So he worked on theory in as much as he thought that there was a basis for or tried to argue that there was a basis for the experiments he was doing. One thing about his book is, he has a treatment of an electron and treatment of matter and a treatment of gravity that is, basically takes an old vector formulation that was done and uses that for his argument, right? So that was one of the things he was always looking for, is a covariant, fully covariant way to explain inertia. And it's known by people that are familiar with general relativity that that general relativity doesn't have inertia built in, right? So one of the things you want to say, if like there's no matter in the universe, if you have a field theory that meets the Mach principle, that you'd have basically no matter, right? Nothing there. So, and that's general relativity. It doesn't work like that. You end up with the de Sitter metric, right? So, it's a well-known thing. So this is definitely Jim was critical in terms of discussions with him. He did eventually. I did talk him into kind of going along with what I was working on. He did at the end agree, and I think it was really great. And he was really excited about things, because this was having this really does push forward what his goal was, which was to get us to be able to have like an impulse type drive, a way of moving without having to throw something back, right? Having to use standard momentum, dPdt type principles. So the other people I want to honor here are John Williamson and Martin van der Mark. They were the founders, I think, of the Quasical Society. And so part of the work that I did is actually adopt the work that they did in terms of into the theory, which was really, really hard, right? So whenever you have a way of looking at things and you see something else that looks weird, right? We have this term cognitive dissonance, right? I felt a lot of that diving into this and doing this work. But definitely, I want to honor them. And there's typos in there that no, it's actually pretty accurate there. Sorry, so I thought there was a typo, but yeah. So the website is not on there, but you can go to quasical.com to see Don Williamson's work and Martin van der Mark and the entire Quasical group. I think their work is really good, and I do use that as correspondence and scaffolding for this theory. So let's get to the program, the meat of this. So part of this effort that I was doing was sort of guided by Einstein's program. So when I say Einstein's program, what I'm referring to is his efforts of having a unified field theory. And it's well known that he didn't really accept quantum mechanics as fundamental. Of course, with any theory, you would expect there to be some kind of emergent thing that would act like quantum mechanics, right? And we find later that we get that, and we get it in spades, and it's once I tell you guys what this is, it becomes very obvious, and this is quite an insight by him, right? Because at the time, quantum was very popular, it was successful, it did a lot of things right, but he held the line, right? So what he was looking for at the time is something that unified all the fields, all the known, we call them forces, call them fields. In modern physics, as opposed to the force type physics, we use fields to describe how forces happen, right? So the field is a more fundamental kind of integrated concept in modern physics. The other thing is he wanted Mach's principle to be incorporated, meaning that it's something that we know. We know that inertia is tied to the distant stars, or the reference frame of the rest of the universe, right? That kind of static reference frame. When I say static, meaning the whole universe as a whole doesn't necessarily on average move, right? It's relatively stable, right? The distant stars. And then also going back to fields is a separate matter source was problematic, right? That's one of Einstein's complaints about general relativity, is that you had a separate matter sources. And of course, general covariance is something you want to keep. So the thing about it is that parity symmetry wasn't discovered until 1956. Now, why do I bring up symmetry? Now, symmetries, when I am referring to symmetries of nature, in classical field theories, those theories are basically, they work the same forward and backwards in time and left and right-handedness, right? You get the same kind of thing. So that is something that is in the mathematics, right? It's embedded in the mathematics of what you use, right? So CPT symmetry is what we know to be accurate now. So charge parity time. So we know that CP is violated, right? PT parity is violated. Time. So if you have all three together, you get symmetry. So this basically, these are discrete symmetries of nature. And so one of the things that we do is we address that in this theory. And I kind of covered these things, right? So matter's source free. So when I say separate fields, we'd like matter to be emergent from the field, right? So a single field, and we have a general covariance, and we want interaction. Okay. So in this theory, basically, we're going to take Sachs's work as pretty much the main scaffolding of the theory. And I'll get into what we do differently than he does. So we take that quaternionic field as fundamental. So this quaternionic field is something which treats time as a quaternion, and each of three, you can call them spatial dimensions, right? So it's really a four-dimensional theory where the dimensions are quaternionic, meaning they have the real part and IJK part. You can think of it that way. So a lot of us are familiar, or some of us are familiar with complex numbers, where you have a real and an imaginary, and you can kind of graph it on a plane, and there's a complex analysis. You can do a lot of mathematics with it, and that's a lot of what is used in quantum mechanics. Is complex numbers are used, right? They're in the equations, but here this is extended, and the reason it's extended is due to the symmetries that we find, right? So in this ontology, in this field-based ontology, basically everything else comes out. The geometry of GR, when I say geometry, I mean general relativity, electromagnetism, quantum mechanics, it all comes out of the field, right? And it's, like I said, this is a field theory. It's not necessarily strictly geometric, but you do have a component or a sector that is geometric, right? And what we're going to do is we're going to take particles as solitons of the field. So there's no separate source, right? Now let's get back to the quaternions, right? We talked a little bit about that. There's different ways of representing quaternions. There's the IJK. You can use Pauli matrices to represent it as well. Now that's one thing Sachs did, is you kind of use them interchangeably. And once you get Pauli matrices, you start to look like you're doing quantum mechanics, right? You start to look like you're doing Dirac and stuff. So why quaternions were used by Sachs, right? Sachs is the one that developed this ontology. I thought I had a slide on him. Maybe I do later. But so Mendel Sachs was the guy that basically developed this theory. And I'll get into what he did that I'm going to do differently. And one of them is having separate matter sources. So why quaternions? So we know about parity violation. And, it does give us an SU2 structure, which is really, really useful, right? And you get, from the structure, you get the symmetries that we expect, right? The violation of discrete symmetries is inherent. So that's one of the benefits. The other thing is, this quaternionic field is deterministic. That being said, determining it is a little bit difficult, right? So it doesn't necessarily mean that it's going to be, you can actually know things, right? So it's a highly nonlinear system, okay? So you're going to find, as you work on this theory, is that you're going to find that you're going to get very high sensitivity to initial conditions, and because of that, things look random, right? So that is something that really comes out of this whole thing. Now, I do want to mention that, you know, the whole thing of nonlinear dynamics and chaos and all that, it's a very popular field, or at least it was for a long time, and that is in spades with this theory, right? So GR by itself is a nonlinear field theory, and it has 10 degrees of freedom, basically. It's and when you add the quaternions here, you end up with 16 equations instead of 10. So it's even kind of, you could say, more nonlinear in a way, and it has more information. So as I mentioned earlier, Sachs had GR and electromagnetism in there, so both field effects are included, and so you get you get mixing and you get other things happening here. So yeah, so the way Mendel Sachs describes his work, and he's no longer with us, but back in you can look on his website. I think it's still there on WordPress or something. But he basically, you know, from his books, and he published a lot, right? So there's a lot of scaffolding there to depend on. Is that he basically tried to follow Einstein's program as well, right? So he took what he thought Einstein would do given the new symmetries of nature, right? And from that, just from doing that, and what I'm showing here is the source-free equation. Sachs's full equation had the sources on the right side, and so he was able to take this equation and actually from it derive GR and derive electromagnetism. Now, the way he did that is it's a quaternionic equation, right? So just like with complex numbers, you can take a number and its conjugate and add them and subtract them, right? You add them, you get kind of the real part, you subtract them, you get the imaginary part. Same kind of concept here, right? You take the quaternion, you take the equation, you take the complex conjugate, you add them, and you end up with the equations of general relativity. You do the same thing, take the conjugate, you subtract them, you end up with a set of 6 equations. And if you have, depending on how you do it, you can end up with source-free equations, which is fine, because in this theory, we get rid of the sources. So we're going to move on. That's one of the things we're doing differently than Mendel Sachs did. And so he did have something else. He did have a background pair hypothesis. So basically, he hypothesized a sea of electron-positron pairs as a background, and that was his mechanism for the Mach effect, right? And we're not going to do that. We're going to actually drop that. So what are we going to replace it with? We're going to replace it with solitonic matter. Now, one of the things in Mendel Sachs's theory, you needed the background pair gas because you needed a way for gamma rays when they came together to basically, he hypothesized this gas where the pairs were in a super low ground state, and gamma rays would come together and they would knock the electron and positron out, right? So that's what his hypothesis was. Now, we're not going to do that. We're going to say the field is fundamental, completely fundamental, and there are no separate sources, and that what happens is when gamma rays come together of the right energy, you end up with pair creation. You end up with an electron and a positron, and their energy and mass and all that stuff comes from their interaction with the field, right? So it's another way of looking at it, right? So I was used to, and I had worked a long time as an undergrad. I discovered Mendel Sachs at, I think it was my junior year, and I read the whole thing, and you know, I knew quantum, and I was, you know, diving into it, and I thought it was great, but the background pairs always bothered me. Also, I want to say Jim Woodward also did not like the background pairs. And I think Hal did a paper that showing that a paired gas or that kind of thing doesn't really make sense, right? So here we find that you wouldn't have, if you create an electron the way the quasi-school group proposes, it actually makes a lot more sense, because if you have solitonic matter, then a lot of what we observe with matter does make sense, right? So it has kind of, we always say it has a wave nature, right? There's a lot of that going around. A lot of people treat it that way, and it's very successful, right? Like Carver Mead, that's. And I also want to say Carver Mead's talk in 2023, the 2023 Kyoto Prize talk, is one of the things that like started me back on this journey, because even though I was looking at theory, I was really not as excited until I saw that talk, and that really like led me down this path to look for something that made sense. So I call it the Williamson-van der Mark electron, and really the work they did was I found it amazing. I mean, I thought it was a kind of a tour de force of inductive logic, of physical logic. Basically going and saying, okay, I have two gamma rays coming together. What if the electron is just that light just spinning in on itself, right? And they call it momentum space, right? So the electron is thought to be that same gamma ray spinning in this kind of like complex, or they call it momentum space, or like a phase space type thing. And it actually works out really well. And the way they describe the way it twists, and that the electric field is always pointing outwards, and that gives you what looks like a charge, right? And you get the spin 1/2 from the thing spinning. Of course, there's mass energy equivalence, right? We know that. And you always get the pair creation from gamma rays, or like, there's also the nonlinear Bright-Wheeler process, which has been observed, but it comes from the energy, right? Creating a pair, and you always get a pair because the charges topologically have to, they're conserved, right? And when you get electron and positron coming together, they unwind, right? And you get the gamma rays coming out. So it's a theory that made a lot of sense. Now, when I first encountered it, like I said, there was a lot of cognitive dissonance in my mind, and I had it took me a while. It took me a while to actually accept it, but it was his Williamson's, and I did encourage you guys to go out on their website, find their YouTube videos, and go watch videos of him explaining things. John Williamson was a particle physicist. He had gone to CERN. He had been around. And I think for anybody doing theory, really listening to people like him that know what they're talking about, that were there and understand the game that is played. Now, I had the benefit of working with Roland Winston at UC Merced, and he was before he did non-imaging optics stuff, he was also a particle physicist, mainly worked on muons. And so he kind of indoctrinated me and taught me about what really people really know, right? So that's one of the reasons I had an open mind about this. So now, okay, so we're trying to figure out, we have this WVDM electron, right? And we're trying to figure out, okay, I'm using Sachs's scaffolding, and we're trying to figure out, okay, how does inertia happen, right? How is it that electron we talked about its formation, let's say it is a soliton. How is it that when I try to push on it, let's say I have an electric field and I'm pushing on it, and it's going to push back? How is that happening? So one of the things that I thought about is that, okay, well, if matter is solitonic light, I went and looked back at, okay, how is special relativity correspondence done in this field theory? And so what I realized was that Sachs had done is he took a very straightforward approach. He just said, okay, well, I'm just going to put a C there in front of the, quaternion that looks like time, right? So I have a quaternion with 4 variables. The real part, I'm just going to say that's C, right? And then everything works out, right? It's great. Now, that's too simplistic. Really what we have is, we know that if I go back a couple slides here, we see that the G mu nu has two quaternions and its conjugate multiplied, right? The trace of that, and with the 1/2 in front. So really, I should be taking the quaternion variable. Let me get back to where I was, and looking at that time component of the quaternion and seeing what it gives me. Now, what happens is I end up with here. I don't have it all laid out, and I wish I did, but basically you end up with a 3-sphere in the quaternionic space, right? So you get the first component squared, second component squared, all 4 squared equal to c squared, right? So you get a 3-sphere, and that's really the constraint of special relativity. So if you're moving in this quaternionic space, quaternionic time component, that's your constraint. Okay, it's not that the first component is c. That's only one part of that sphere. So now when I open that up, I actually figured out that, and that second equation kind of shows you that I have special relativity requires that the time component has this c and this I call it exponential. It's kind of unit rotor, right? So if you guys are familiar with complex numbers again, right? So you can have a complex number x plus iy, and that's a point. You can have a circle, and that can be represented by an exponential of a radius and just an exponential of some time or some, right? And then that radius is explained in the unit sphere where you have the I up there, right? So e to the I t or whatever. And that gives you a circle in a quaternion space, right? So here, I mean, in complex space. So here we have a quaternionic sphere, 3-sphere, and that really is what special relativity really constrains the theory to be in, right? To have that there. So in Mendel-Sachs's field ontology, just like with general relativity, you have your field, right? Your G mu nu or metric, and then you have your affine connection that you calculate, and you have your general equations, right? So in Sachs's theory, there's something similar. There's something called the spin affine connection. That's the omega down there. So one of the things I did is I said, okay, well, if I'm going to take Williamson and van der Mark's electron, and I'm going to bring it into this quaternionic field theory. And by the way, I want to say something about their theory. Their theory is based on a Clifford algebra. It's very compatible with the algebra I'm working on. And also about that algebra, the algebra I'm working on can also be, there's tons of ways of writing these things in terms of algebraic identifications. So a lot of them are compatible. The good thing about this is that it has that symmetries built in, and that's why I'm kind of sticking to it also for historical reasons, right? I want to make sure that connection to Sachs's work is really strong. That being said, there's other ways to write this, right? So now, okay, getting back to the story here. So the correspondence with special relativity here gives us a spin affine connection that basically applies to any particle, any wave, anywhere in the universe, right? So we know the speed of light is the speed limit that light has, right? So this applies to the light, but this also applies to solitons, right? And what this does is actually when I don't know if I'm giving away things, but basically this actually took me, I was even like working on this yesterday, like getting this to this state. So it's something that is persistent. Now in terms of what this operator is, you want to think of it a lot like the affine connection in general relativity. So something that carries the force or the field. So I'll give you an example. In GR, like let's say you have the Schwarzschild solution, so there's a planet or a star or something, and GR explains the way gravity acts. When you're far away from the star, you're no longer touching, right? So that field extends. And the way that extends, when you do the calculations of the field theory, you do have to take the affine connection and calculate that out to actually figure out, how you're being acted upon by that field, right? So again, this is the way I'm treating this is a background structure that's basically pervasive through all the universe. So I'm looking at special relativity, knowing that the speed of light is a universal speed limit everywhere. You have the speed of light everywhere in the universe. So this field or this connection exists everywhere in the universe. Okay, that's how I'm looking at it. Now, what this buys you is that if you have solitonic matter, it now gives you a reason why that matter carries inertia. So when you try to push that electron, it has to move in that field, and therefore it gives that whatever push you gave it, it gives you the exact same push back. And if you take this thing and you actually there's two main things I looked at in terms of correspondence. One was Carver-Mead's recent work, the engineering view of gravitation, and it slots in perfectly with that, and also the Cook and Siyama condition comes out as well. So it works out really well in terms of the relational, Y inertia, right? The whole thing about the Reisner's hypothesis and like all that stuff. It makes a lot of sense now with this, because now you have, basically Reisner's hypothesis was that there's some kind of motion internally to the electron, and that motion was giving it inertia. Well, now using the solitonic model for matter, that inertia is that light spinning in that momentum space, right? That's the spin. That's the motion that is going on. And so, but it's a field, right? So in the quasical theory, there is no background field, right? It's in terms of that, it's a linear theory, right? So it doesn't have the same connections that the spinifying connection as I write it here. It doesn't have the commutator that you're seeing right there, okay? That nonlinear part. So so that is now there. So this in an empty universe, and the cool thing about this is that if you do the thought experiment, okay, what happens if I get rid of all the rest of the universe, and my spinifying connection goes to zero? Well, there's nothing holding that electron. It'll just decay into a gamma ray, right? So you'd have one sad gamma ray moving through space, empty space, right? So if that really gives a good closed form. I mean, this is kind of like the punchline in terms of like inertia. Now, the other thing is that, this was the point when I found this out. This was probably, I was really excited at the time. I forget what month it was. It was April or May or something. And Jim was pushing me to publish. And I was like, well, one of the problems that I had with the solitonic model is the stability, right? So part of my work at UC Merced, I was in non-imaging optics, so I studied light a lot, and I knew about nonlinear materials. I knew about the fact that you could trap light and you can get solitonic light to persist in material, right? But those were nonlinear materials, right? So I was looking at what I had, and I was realizing that, hey, I don't have anything that like supports such a strong, stable particle like the electron, right? The electron is one of the most stable things we know, right? It is, right? So if you hit it with anything, it blows it up, other than a positron, right, which unwinds it. So it's a very stable thing. So I had to rack my brain, and I was trying to figure out, okay, what do I need to do? So eventually I figured out, okay, what if I, not just special relativity, but what if I got correspondence with the basic tenets of cosmology, the isotropy and homogeneity, right? So the universe, the big scale is the same in any direction, right? And in large scales, it's pretty much homogeneous, okay? So that's something that actually Sachs had worked on. And so what I did is I said, okay, I'm going to make the same move. I'm going to take my quaternionic field and make the same assumption that Sachs did, and then I'll take the spin-affine connection, actually calculate the spin-affine connection for that. So I got something that, if you look at it, you'll notice that there are not just time components, but there's spatial components. So when I saw that, I realized that now I have something, and by the way, the bottom only shows the time component, up top, and the second bullet at the end is the spatial component. So now I had something where not only do I have like the inertia described, but I also had a reason why the electron was stable. Okay, and you know, it was, for me, it was, you know, especially the training I got from Roland. Like I really wanted to figure this out before I published this. I really wanted to have a physical, you know, down to earth reason why the electron was stable. Okay, so if you guys know about, you know, light and there are ways of getting stability, but a lot of those don't have, you know, they're basically null. So they don't have like electric fields pointing out, right? So the electron really needs something for that. So what I found, and this is, I also need to mention Arnie Ben, because Arnie Ben was kind enough to share a preprint with me. And I'm not sure yet, I haven't talked to him recently about whether that was published, but where they took that electron and actually put it on a torus. And that whole thing really came to me in terms of like my training in nonlinear dynamics and chaos, because that's something I had studied. And it's not a standard curriculum, but for physics, but it's something that I did. I was really interested in that. And I realized that is actually what's going on, that the electron is exhibiting what's called KAM. It's an abbreviation for the people that figured this out. This dynamical stability in this nonlinear field basically creates a tori in this quaternionic space or momentum space, however you want to call it, that persists. So basically, to get it out of that, because of the way that stability condition occurs, to get it out of there, you have to actually, that's why you need a positron to destroy an electron. Nothing else will do it, right? So this realization really made the field theory a lot stronger in terms of like, okay, now I have particles that are arguably stable in, you know, universal lifetimes. And so, and also this generalized Mach principle was something that Mendel Sachs had come up with. He actually proposed that not just the mass, but the charge, the magnetic moment, everything had to come from a coupling. Matter had to couple to the rest of the universe, and that coupling had to be, you know, there had to be some reason from that coupling for the properties that we see, right? Because you're doing a field theory. So that's kind of logically have, you know, you to be self-consistent, you need that, right? So that's what was discovered here. So basically topologically, right, you have this thing spinning in a torus, and it actually has this dynamical stability. And again, it's if you don't touch it, it's not going to do anything. You try to move it, it's going to push back, right? And that pushback comes from that other thing. So yeah, so the CAM stable electron. Now, one of the things is I do have here the golden ratio for the tori ratio. Now, that's not necessarily final, but it's supposed to come from, you know, basically energy minimization. So it could be this, but there's other stable regimes that you could get. The main thing is that the stability is, I mean, it's highly stable. And the other thing I want to mention is that in terms of the charge that you get in Sachs's theory, Sachs already had kind of derived topologically that the charge needs to be exact. But here we want to make sure, like, as I write the paper, this is something that I'm, you know, there's going to be here I'm mainly addressing inertia, but also, you know, I'm figuring out what the electron really is at a deep level, and we need to get those numbers correct, right, as we go along. Now, one thing I'll say is that doing the math for this is pretty difficult, right? So this nonlinear dynamics and all that stuff is one of the it's kind of like depending on how many dimensions you go, it's kind of like the known border of knowledge, right? So now the proton. Okay, this is another. Once I figured out the electron, or thought I did, the proton is what came next. And Jim was pushing me. He's like, you got to publish, and I'm like, well, I need to figure out the proton. He's like, you can't solve everything, and so there's models where you can take, if you have the tori and momentum space for an electron, you can say, okay, maybe it's some kind of a knot, right? That's a lot of what's out there, and interestingly, a lot of the modern knot theory I found out after doing some research was came from back in the day. Lord Kelvin had hypothesized, right, knowing E and M, that maybe matter was solitonic electromagnetism, right? But of course, he was dealing with, at the time, the popular theory was the whole background, persistent background thing, right? We don't want to talk about it anymore. but he so because of that, people started to do knot theory, right? So knot theory was something that I thought of for a while, and the reason why is that protons are known, and the neutrons and all that type of matter, baryons are known to have internal structure of some type, right? But eventually, I came across the scroll ring. Now, scroll ring, one of the books I studied, nonlinear dynamics, I still have that book from a long time ago, first edition of Strogatz. The cover was a scroll ring. And when I saw that, I realized that's exactly what I needed, because not only do I need something that is very stable, and you find that the tori of the electron is a very stable thing. It needs to be almost infinitely stable. There was one of the members of the classical group, Vivian Robinson, had come up with a theory where he was treating a proton as also like an electron, like something that was made out of electromagnetic energy, but it had harmonics to it, right? A 1 1/3 and 1/9 harmonic. And so a scroll ring fits that perfectly, right? So you can build a scroll ring where the scrolls internally it's like a torus that's nested with a similar, I wish I had a graphic, but you can look them up. And so the scroll ring actually made a lot of sense for a proton. And actually, once I did the math, I got the stability I needed. I got everything. And you get the magnetic moment. All of it works out and aligns with Robinson's work. Really, it's a really neat fit for that, because one of the things with Robinson's work is he does it at a kind of more straightforward mathematical level, which is fine. And you guys will note that if you go to the classical website, you'll note on there that they build out, nuclei of atoms based on these models, and they have a whole table of elements and all that stuff. So if you guys are interested in that kind of stuff, I would highly recommend looking at their thing. I don't know how much this is going to modify that. This is one of the things. The proton is not. I'm not saying I know for sure. This is more okay. I have a strong inkling that this is the direction it'll go because of what happened with the electron, and definitely a follow-up paper in the future needs to happen with all the particles in terms of like particle stuff. Now, but all that being said, that is not the focus of this theory, right? Although you need matter, right? So one of the things about this, though, is that having these two as structures that come out, a toroid and a scroll ring structure, it makes a lot of sense why those are the only two matter particles that are stable, right? There's no other matter particles that are long-term stable. Even the neutron decays after like 880 seconds or so. So this really brought to me the fact that now I have a strong understanding of why things look random, why nuclear decay looks random, why a lot of this stuff is random. And by the way, one of the reasons for Sachs's background pairs is he used that as a source of randomness in his theory, which makes a lot of sense, right? You have a background pair C, you randomly collide, it could cause randomness. So here with this, and the way we're treating these fields, we don't need that, right? So we already have a source of random. The nonlinearity of the field itself is a source of randomness, right? And the sensitivity to initial conditions is really. Now, one of the things that happened as I was working on this theory, and this was after the proton, is I said, there was a paper done maybe about 10 years back or so, where someone took Sachs's work and they did a Schwarzschild solution, fully. Sachs had one, but he kind of like didn't show all the steps in his book. But he showed correspondence. He showed that, okay, you get the standard thing. He did some extra steps. But these guys, they took Sachs's theory, they went over it, and that's one of the references in my paper. And they actually recreated the Schwarzschild solution. So I thought, okay, well, I should probably do that, right? So I have a background spin-affine connection that I need to apply, right? So I'm saying that background spin-affine connection is persistent throughout all the universe. So I should probably do this. Now, once I did that, I ended up getting an extra term, and that extra term had an r squared and had an h squared over c squared in it, which is basically what I recovered was the de Sitter-Schwarzschild metric. And that, I wasn't expecting that. I should have expected it in hindsight, but that surprised me. So I said, wait a minute. Now let me go back and I'll take the background spin-affine connection I have and take it through the rest of the steps, right? So in Sachs's field ontology, you get the spin curvature, or I'm sorry, the spin field, the q, the little q, and you take that and you get the spin-affine connection, right? You derive that, and then from there you go to the curvature tensor, and once you have the curvature tensor, you put it into the covariant field equations, which I'll go back to that slide and show that right here. So that's the K, right? And so you put that in there, and the little q, you put those in there, and you figure this out, right? You solve this for R. And so I went and did that, and I ended up with something I didn't expect, which was the Friedmann equations. Now, I should have expected it. And one of the things in the Friedmann equation is that constant that has the h in there, which is traditionally in GR, is inserted, right? Basically, that is the cosmological constant. So it was not something inserted from the beginning. It was just, it came out of the quaternionic structure. So that was surprising. And of course, here I'm not using quantum field theory, right? That's not fundamental here, even though it's UQFT, unified quantum field theory is what I call it. It's not quantum field theory. That's a different theory. So there's no vacuum catastrophe, and you get the Friedmann equations, which was really nice. It was a surprise for me. I didn't expect it, and of course, I think this happened. This is one of the last kind of major thing. Well, it's not the last one. There's other things that when I dove into the particle side of things, I found a lot of things that were really, really exciting and fun. But I kind of had to dial back. I was having a lot of fun kind of discovering things like this from that basic assumptions of the theory. And, that probably caused me to, spend time doing that as opposed to writing the paper and all that stuff. So let's get back to inertia. So what this means for inertia. So inertia, we find, is a coupling of the matter solitons to the cosmic background. Now, I'm not going to say, in terms of the cosmic background, I did, throw in special relativity, and there's the speed of light. And I want to mention that the way I look at the speed of light is I look at it as the wave speed of the field, right? So now, can we derive the speed of light from something more basic, like maybe if we measure the average density of the universe or something like that? So possibly, right? We could potentially do some things to like even further lower the number of constants in nature, but that's not the focus of this paper yet. That might be a future paper. For this paper, for now, the matter, the mass of particles are directly due to stability coming from the energy content, right? And that energy content is what interacts with the field and pushes back, and that's what they have. So that explains what mass is. And so the whole thing about, okay, there being a special number, it's not the case. It happens to be, that is what happens to be stable in our universe. Now, if you think about it, the universe has that background. It's consistent everywhere, right? In a big enough structure, you get and that's why it's C, right? It's a very big number. So that background determines both the stability and, of course, that number, I said driving expansion, but it gives us the dark energy factor we see. So, by the way, when I said the Schwarzschild solution, one of the things with that, when you have the R squared, is that term is what you use when you look at the redshift of light, right? So you take GR and you look at light coming from a source, like let's say just above a star, and coming to you billions of light years away. When you put that number in, you start to get that redshift term interact. Otherwise, that H is over C squared is a really small number close to the star. You don't see that, right? You don't see the de Sitter effect. You don't see the cosmological effects. So that's what is explained by this theory. Jim's effect, I call it the Woodward effect now. He used to call it the Mach effect. I think we should rename it after him because Mach didn't think of this. Mach thought of the Mach principle. But the Woodward effect is something that is plausible in the theory, right? So I did do a paper and send it to Jim when he was still around and show him how, I could reduce and get correspondence with the way he was deriving this. Now, I might have different terms. It's not necessarily exactly the same prediction he had, but the way he was doing this is something that could potentially work. I'm not saying it does for sure, but it could potentially work. And of course, now having matter, and one of the things about quasical is like you look at the electron, the way it's formed, when the way it's formed gives you a charge, gives you a mass, right? This whole quantization thing is emergent, right? So not only did Sachs have in his writings quantum mechanics and the formulation of the direct equation and all that stuff coming out, so did the quasical group, right? So if you look at their formulation, it's you can consider it an extension of the Dirac equation that includes E and M. And I mean, it's really, I would encourage anyone to go through and watch the lectures of that group. And of course, we have a single quaternionic field, source free, is fully covariant now. So that's where we're at. And that's the last slide I have.
Curtis, that is awesome. That is awesome. Thank you. Thank you. Thank you. Thank you. And I love it that you were honoring Jim Woodward also. That is so giant. That is so giant. Okay, so let me, if it's okay, let me take this. I'll just take it down for a moment. Let me bring everybody in. Guys, let's give an enormous applause to Curtis Horn. Curtis has been burning the candle at both ends. I've been in touch with him. He's been trying to present actually for a couple of months. He's trying to archive all of the materials that Jim had, right? I mean, a career's worth, a lifetime's worth of research, as well as technical stuff. He's trying to find a home for stuff. He is super involved with that. He has a family. He has a day job career. And the unified field theory is his own work. So he's juggling like a ton of different stuff there. And I am just overjoyed that he was finally able to present on this. So Curtis, thank you, man. Thank you.
Yeah,
Thank you.
thanks. And it was great to have this deadline because I got to post on archive this weekend. I almost have the paper ready. I just I'm like formatting appendices. You know how it goes. So I don't know.
Yeah, I'm right there with you. I think all of us are doing that, right? It's like that year-end rush. I mean, I'm juggling like I'm quite literally juggling about 15 different like half projects, and then wrapping Christmas presents too, right? When I have time. So
Yep.
Yeah. Although the advantage you have is you are in the Los Angeles area where you have sunshine. Like
Yes.
Nathan, he's got sunshine.
Yeah.
We have a solid month of rain in Seattle. It is just like yuck. So
all right. So,
yeah.
Let's see. Anyone have questions?
Curtis, how does this help us build a widget?
Well,
you're a widget builder. You took a couple of months off to do the physicsy nonsense. Now, how does it build a better widget?
Yeah. Well, I like I said, I haven't looked at your stuff and application. I did look at Jim's, and Jim's is definitely possible with this in terms of doing inertial propulsion. From my first inspection, I haven't looked at your theories. All that being said, what it does inform us, if this is right about matter, is that I mean it does kind of like, this is one of the reasons I was like taking a step back from this whole thing about warp, just using GR, because if you understand that matter is basically a solitonic photon or gamma ray, right? The warp might not help you, okay, the way you're thinking about it. So there's a more basically there's a more fundamental field. So I don't know if warp is possible or not. That's not something I've gotten into. I mean, this is really what I've been doing, Drew, is really hard. Okay.
I believe you, brother, but
hard time.
Again,
well,
so we already had theories that talked about stuff. You have another better, hopefully way better theory that talks about stuff. But
well,
okay.
So the thing is about those theories
something off of it?
Is they were not compatible, right? So you didn't have, you had to like take limits and do a bunch of guesses, and so with this, yeah, like I think one of the things with what we had before when I was in the lab doing the stuff with Jim, is that we had sort of guesses as to like what it should be in terms of the reaction we should get. So I think here I might get a better idea of, okay, if it is possible to do an inertial drive, maybe the theory is a little bit different, the way I build the structure, right? And the way I'm putting stuff in there. So definitely I'm going to be using this as opposed to the old stuff for the work I'm doing, continuing on in terms of the stuff in the experiment. So I am going to be doing that. That's next. That's a whole nother paper.
So one thing I had wondered was, you have been promoting Carver Mead's work, and I've gone through his work, and I fed it into GPT also, and I asked it if it could do kind of a condensation or summary of it, and it came back and it did actually a really interesting summary, but it really indicated that it wasn't highly actionable, which goes to what Drew is saying. It's like, okay, we have a cool theory, but there's not a lot that we can put this to work to build. And that was, I actually felt bummed out, because with Carver Mead, it had a couple of ideas to test things, but it didn't seem like it had any smoking guns in terms of do this and it will create motion, And so I wondered how much was your work, I guess, informed by his ideas. And then another question I should ask is, you have talked about the quantum tricycle, the quicicle, if I remember right. And that's Arnie's group, and Vivian, you pointed me towards them. How much have their questions about the underpinning of physics informed your work?
I didn't catch the first. It kind of broke up. What was the first person you said?
Oh,
was that Jim?
Sorry, yeah. So Carver Mead. I was wondering how much Carver Mead and the quantum tricycle bicycle group.
Carver Mead was basically when he gave that Kyoto Prize talk. That kind of like set me back on the path of doing theory, because he kind of put out that challenge. Like he went over a bunch of experiments that were very interesting. One of them was when back in the 70s, they took some neutrons and did a neutron diffraction experiment and had that diffraction be variable with gravity and with the rotation of the Earth. And that experiment really showed that the Mach principle was a real thing. And so that was, that kind of like was more motivational for me. Now, part of his work is that engineering view on gravitation. I don't know if you know who Carver Mead is, but he's like the inventor of VLSI, like a lot of what we have in terms of computation. And he wrote a book, Collective Electrodynamics, back in the early 2000s. He's out of Caltech, and so his view was he was taking matter as waves, and he doesn't talk kindly about quantum mechanics. You can go see his presentations, and he treats matter as waves directly, and he has in his formulation of matter, he has the Mach principle like built in. So his theory is one of the ones when I built my work, I made sure I had correspondence with his. So motivation and correspondence with it. In terms of like the quadricycle group, that was one of the main structures that I needed to put this together. So the way I see it, I have Mendel Sachs's work, it's main scaffolding, but also the whole thing about understanding an electron and it being like, not just a hand wavy thing, right? So there's a lot of models out there where they take an electron and okay, we'll treat it as a wave, and kind of like at a light level, just put a wave equation, a generic one in there, and have whatever. Theirs was very specific and very, like I said, it's like a tour de force of inductive physical logic. So that was, me going and like getting over the cognitive dissonance of okay, can I have fields that like persist? And sure enough, yeah, you can. So that was a big thing that helped me kind of complete the whole thing.
Okay. And so if Mach's principle falls out of it, then maybe like what I'm trying to kind of wrap my head around was with Carver Mead stuff, he hasn't maybe applied himself directly to, hey, I'm going to solve propulsion, but solutions are kind of hidden in there. You just have to tease them out.
Yeah. So like I said, I mean, as you know, I work with Jim, and so Jim's kind of move of having both the Mach-Lorentz thruster and the mega drive. Those are the two known solutions that Jim found that look like both of those should work with this theory as well.
Yeah, that is awesome.
So I'm going to continue that work based on this theory, and like I said, I might get different predictions that Jim did. So in terms of the practical side of the experiment, you got to remember we were doing stuff with like a dumb function generator. So we were not getting, we were not putting any kind of sophisticated waveforms in there, and we really needed to do that. So there's a lot of improvements that need to happen with the experiment.
Well, and that is intriguing. That's actually really intriguing. And that was one of the things, Drew, I remember when I came to visit you and Charlie had talked about that also, that's untapped territory for you guys is AC waveforms, right? That it's out there in the future. It's something to build with. Yeah, I mean, amazing stuff. Do you guys have any, Nathan, Joel?
I do.
Drew?
I do, please. So Curtis, hello, by the way. Haven't seen you in a while. Hope you're doing well. Curtis and I, by the way, as a quick side note, I kind of view us as like two ships passing in the night because we were both at UC Merced at one point, and we both have interacted with Jim. He worked with Jim Woodward extensively. I did not nearly as much as he did, but I did have a fair share of that, and that's where my question's coming from. I gave my best shot at trying to study and even validate Jim Woodward's theoretical work. Obviously, I work in theory, not in experiment. I get the sense, Curtis, you actually have your hand in both. But I know Jim was very, very adamant about that his theory and his predictions are fundamentally rooted in general relativity, and he wasn't fond of the idea of anything outside of general relativity being an explanation for his work. Though I must say, as a bit of a caveat, he did use work like from Sciama's paper that was not general relativity. But anyways, it's a long story, obviously, and you know it, I'm sure, better than I do. The only point I'm trying to ask then is, you mentioned, and it really caught my ear, that the theory you're working on right now would potentially explain Jim Woodward's predictions, and I assume maybe experimental data. So I suppose what I'm curious is, first of all, is that something you did despite his insistence that we should use purely GR? And also, please elaborate on how you were able to validate his theory.
Okay, so those are great questions, Nathan. I think yes, it took some time working with Jim to convince him that he understood that GR didn't have the Mach principle in it, right? It's something that we know that that's not there, but I think what he was hoping for is that that somebody would extend it in a way, kind of like Sciama tried to do, right? In a way where it could you could still get it, and that's exactly what I've done, right? So now the thing is, when he's insisting on that, he's the thing about a lot of these theories, like we look at them, they're like vector formulations, right? There's tons of those vector formulations of gravity that we know that are Einstein was doing them too, right, as a start, and so he had to do that. So what he was trying to do fundamentally was get the general covariance in there and as something compatible. And at first, how Jim was. He actually even used to tell me that he would tell Hal not to work on theory, right? He'd tell all of us not to work on theory and just concentrate on experiment, because that's the only thing we could do. And so at some point I just went ahead, because I figured there was something there to find still. And so
experimentally or theoretically?
Theoretically, right?
Okay.
And so now with this theory and having a basically a connection that causes inertia, I mean, at the end of the day, Jim was convinced, right? He agreed with it. He was pushing me to publish. He was almost spilling the beans to other people. But he did like this, and yes, so I did do a derivation where I found that I get correspondence with Jim's formula, where the delta M type thing, right? So
yeah,
and the reason it works is because what he's doing is that he's not actually manipulating the inertia of matter. He's manipulating kind of like a bulk aggregate in an asymmetrical way that gives you the effect, right? And so I now that the theory is done, I want to go back and I actually derive it from the theory strictly, right? So that I can see okay, maybe there's a regime that's better or something like that, right? So, but for me, the fact that there is some kind of connection, is helpful. Like, as you know, one of the theories that were out there was the whole Nollikar type theory, which is like taking waves from the future, right?
Yeah.
Electromagnetic waves from the future, right? So the thing about what I'm doing is I don't need any of that. It's a persistent background, so it's already there. So it's throughout the universe. It gives us stability. It gives us, the speed of light. Everything's there, and that's why we have inertia. And matter is, matter is just light, solitonic light, and it might be uncomfortable, but that's what it is. We're stable, and
I wonder if there's I'll just put it more concretely. Like when I worked on the theory, and maybe at some point, maybe if Tim invites me to give a talk on that topic, I'd be happy to do that. Because I prepared a whole presentation on it, because I worked with Jim for a couple of years on and off. And you might know Lance Williams. He also was trying, and Jose Rodal, and so we all bounced ideas. And so I basically just kind of approached Jim and just said, okay, tell me exactly what are the presuppositions you want, and then I will go to general relativity and see if what you're looking for comes out. And what he wanted was a scalar potential that permeates the whole universe and is equal to c squared. So it was large. But he also wanted to see an equation of motion that matches what you get from linearized general relativity, which requires a small gravitational field. And then he also wanted to basically have a mass energy manifest itself by introducing like an oscillation. And you understand obviously the intricacies of that part. I never even got that far, honestly. The only point I'm trying to make is I have to assume that you must have left some of those ingredients out somewhere, because I'm convinced personally, when you put those together, you don't get the result that he wants. And
that's not a starting point.
I assume.
Yeah, that's what he's giving you is the ending point, not the starting point.
But he also wants certain ingredients. So he's like, I want my meal to taste like this, and I want you to put this ingredient, and this ingredient. I'm like, no, I'm like, if I put those ingredients, it just doesn't taste the way you want it to. Like, I'm sorry, like I don't know what to do about that, And I found other ways to try to get there, but they would always result in issues that weren't satisfactory to him. Like, for example, inertia turned out to be a result of Hubble drag, and that was not desirable because that actually causes your system to lose momentum to the gravitational field of the universe rather than gain momentum from the gravitational field of the universe. So one way or another, I always ended up in this predicament where it wasn't arriving at what he wanted to see. And so I would love if we could compare notes one day, or maybe do a joint talk, maybe like a Woodward tribute. I know it's awkward because what I have to present doesn't like validate what he wanted to see. So it's a bit of an awkward tribute, but maybe at some point we could do that, like just for finality's sake. I mean, I know there was an APEC talk where we did something like that. But where you presented actually sort of a tribute to him, but I mean, we could do something technical.
Yeah. Well, I think my comment would be that, he was giving you his like wish list, but in terms of like getting there, it's one of those things you have to take 2 steps back to go forward. And so just assuming GR is by itself is only a sector of this theory, right? So we know GR doesn't have the right symmetries that we know nature has. And that's, and by the way, I didn't mention this, but one of the other things, and it's going to be in my paper is pretty much done. I'm going to try to post it on archive either tonight or tomorrow. But one of the other things I found out about, this was after, I think after Carver Mead's talk, was that there's a YouTube channel that I always watch, Cosmology Talks. They have like great presentations on things that they find in cosmology. And there was a presentation where they had discovered that there was parity symmetry violation in the large scale structure of the universe, like some ordering of galaxies or some such. When I heard that, I was like, oh my goodness, I got to go back to Sachs's work. That's what kind of led me back to go to Sachs's work. Now, if you talk about GR and you talk about Sachs's work, those are 2 distinct different things, because Sachs's work is what you would do if you were trying to develop GR, knowing that the symmetries, the parity symmetry and the discrete symmetries are not fundamental, right? So you throw those away and you get a different mathematical group. And that's why you get electromagnetism and gravity kind of popping out. And now just taking that on its own and doing correspondence with special relativity and cosmology, you already have a mechanism for the Mach principle. So, I mean, it's not a path that Jim like Jim and I had a few arguments about it. He's like,
Oh, I don't doubt that.
He was like, Curtis, I don't care about symmetries. I'm like, well, you should, because that's how you know what algebra you use, right? So
his favorite was to quote Einstein's sentences. So it wasn't really his thing to try to get into like the analysis in that respect, but at the same time he wanted to see it done. So I really wanted to see it happen for him and help with that. That would have been amazing.
Yeah, he did know basically all this development. He did know all of it before he passed away, which is really great.
Oh, so that's interesting.
He knew about it. He was emailing people. Yeah, Curtis's field theory. I'm excited. He was.
Oh, yeah. So you had his endorsement on that.
Yeah.
Wow.
Yeah. So, but yeah, it's too bad that I was trying to talk him into like both of us being on the paper, but he said just put me as an acknowledgement. You know how he was, but yeah. So.
Well, thank you for clarifying. I was very curious about that.
Yeah. Yeah, but no, we do have. If matter is solitonic, if it's light, then the speed of light is what constrains it, right? So, so that's where it just comes out. Joel, did you have a question?
Yeah, actually a couple, but I'm just thank you very much for the presentation, and we had some talks about your framework and theory already, and I really enjoyed it, and I'm again looking forward to seeing the whole paper. And it's quite late here in Germany, so my head is spinning. Yeah. Also, we had this is something maybe to Drew's point, to go back to that for a moment. We have made, I think, incredible strides in the theoretical field. So we have multiple very different theoretical frameworks openly discussed, which are going beyond the mainstream framework, and we're actually trying to connect them to the experiments. And for example, I got Drew's data set, and I'm trying to actually map Heim's theory to that data set and show, is it right or is it wrong, and do basically what physics should do, right? Test the models in reality. And it's also great to see that your theoretical development was highly influenced by what you did on the experimental side, right? So I think these are all very big steps in the right direction to do more informed experiments, and then do the next step and do even way more informed engineering, and hopefully within our lifetimes to go beyond what Drew is already doing. Like, he is already doing what we're all into, novel propulsion, but we need to get to even more sophisticated technology if we want to build a real warp drive kind of spaceship, right? So the theoretical steps forward are totally necessary for that. And it's really great to see so many people with great ideas who are probably also quite interconnected share their presentations this year here. And so to go back to my question, I have a couple actually. I wrote some of them down. I'm gonna start, or maybe just go with this one. So you derived the fine structure constant as well, right? So we talked about. I just wanted to clarify that point.
Yeah. So I did not focus on deriving other constants other than making sure that I had like the models for like the particles, like the electron and the proton, that I get the constants expected there. I sort of kind of like looked at other constants here and there a little bit, but I didn't focus on that at all yet, because that's like a that would be
it's
another...
also totally fine. Like I understand that the math is really complicated, and as I told you before, it's great that you publish, and then multiple people can look simultaneously at this different kind of broad yes application of the framework, right? So yes, I want to how do you recover the color confinement? So basically, so what replaces the gluon gauge field in the soliton picture, especially? Have you looked into that?
Yeah. Well, if you're, I mean, if the proton is a scroll ring, then there's no way to get anything out of there, right? It's just a property of the structure. So a lot of the properties that you would normally, that are kind of like
I see.
problems.
It's just a structure. Yeah, that's a very, very similar solution to Heim's framework. It's very interesting.
Yeah, and I would encourage watching Williamson's talks on, especially on this stuff, because he was at CERN for a time, and so he knew very well the particle game where you're having, it's almost like the table of elements, right? So the model has a bunch of different factors that you can tweak to keep the model consistent. So it doesn't necessarily give us So here now we have something where, okay, we know it's a nonlinear dynamical system, and we can apply that mathematics to actually give us predictions and figure out how we do what we want. So Drew's question about, okay, what about motion? Like, okay, that's something we're going to address, but actually this framework and this theory gives us insight into matter in a way that there's a lot of other applications that I'm looking at, right? So I haven't talked about holonomy, I haven't talked about imaging. There's so many other communications. There's like so many aspects that this can affect now. Multi-messenger signals, like why is it that we get the same things come at the same time, right? When you're looking at gravity waves and light waves, right? So a lot of this stuff falls out.
Mm.
Did you have another question, Joel?
I could maybe go on, but it doesn't have to be today. I really, if I've got your paper and can spend some more time with it, sure, I will definitely come up with some more informed questions, especially if it's not 4 o'clock in the morning. And
right. Oh. I understand.
Yeah, well, and time of year and all of that, right? We've got a lot going on. But I'll tell you, I'm overjoyed. We've had some amazing presentations today. So if you guys are set, why don't we'll give Curtis another applause, and then if anybody has lab demos, but let's start with that. Curtis, Mr. Curtis Horn, thank you. Many, many, many thanks. I know that you pulled out all of the stops, and I want to thank you so much for doing that, for making this come together. It's amazing, man.
Yeah, so I just want to give you an update on the lab. I guess it's time, right? So
yeah, here,
so
I'll spotlight you.
I pretty much the previous Friday, we had some movers help me move everything to the new space, and so there's still stuff there. I got to go back and make sure I get everything else that I need, but pretty much everything is moved. So yeah, I think we're going to be in good shape. I do want to get new equipment, get a new vacuum chamber, build the structure like I think it should be. Of course, I got to work on the theory and make sure that, okay, I still predict the same regime for things to work, but yeah, I in terms of the experiment, I'm excited, and I think that that's something that I'm going to continue doing for sure. So
okay, let me see. Sorry, I'm fighting with my mouse here. Having trouble with the unmaximize button. Yeah, Curtis, one thing I wanted to say, and I'm absolutely serious about this, is the work that you were doing, not only your own work, which is continuous and ongoing and changing the world, right? But like the work that you're doing helping preserve Jim's legacy is absolutely invaluable. And all of us are doing similar things. And I know that, right? Joel is in the same boat with Heim theory. You know, and Nathan has had, I'm sure, Nathan, you've probably had several mentors who have passed on, right? So,
actually, fortunately, I have not. I'm very grateful because Ray Chow is alive and very active, and then all the colleagues that we work with together. Yeah, so Curtis, I genuinely like sympathize with how challenging that must be, like having your advisor, because that was your PhD advisor, Roland Winston, right?
Yeah.
And then Jim Woodward being your basically supervisor, I assume, for a period of time, right?
Yeah. Well, actually, it's a funny story. When I was at when I was at Cal State Fullerton, before I went to UC Merced, Hal was my advisor. So Hal, because I wanted to do a PhD program, so Hal was like, "Don't work with Jim because no one will accept you." At the time, so you know how it is in physics. Like people are like, "What are you doing that goofy stuff for?" And then,
you don't really want to do a PhD with like a very outside the box topic, if you right.
That's the advice. But what happened was so Hal went on a sabbatical the last year I was at Cal State Fullerton. Then when I went to UC Merced, I come back to visit and I find Hal working with Jim. And so I was like, Hal, like you're like, you told me not to work with Jim. I come back here, you're working with Jim. So I used to keep in touch with Hal and like, give Hal advice, give him advice about things. And so like when they were trying to model stuff, I recommended COMSOL, and I used to try to help them out. And in terms of theory, I would talk to them about Sachs's stuff. But that, Jim did not like the background pairs. No one liked the background pairs. So I'm glad that we're rid of that. And now it's like a field theory that Einstein would have probably liked, right? So that was a big thing. And Hal now is retired. So Hal basically like doesn't really talk to me about physics anymore at all. So there's that as well. So I'm kind of out here on my own.
Yeah.
Ray, I did meet him a few times at Merced, but he wasn't. I didn't work directly with him. So
he's retired, so he's just pure research now, without even actually PhD students.
Okay. Yeah, one of the cool things in this theory is that the holonomy, you get like Abramoff-Bohm effect and all that stuff pops out from one equation. So you don't have to have a bunch of different, the Sagnac effect, all that stuff is just like really easy. So it's something that he might be interested in.
That's true.
He did work on that, kind of like the Abramoff-Bohm effect for like light, right? Remember?
We just published a paper like just earlier this year, I think it was, or maybe last year on that. A couple of papers actually, an electric scalar Aharonov-Bohm effect and a gravitational Aharonov-Bohm effect.
Yeah. So that all pops out of this when you just do the holonomy of the field and you get all that. It's really, I mean, all of the, depending what sector you're using the theory in, you can get all that stuff. So anyway,
I'm sorry to derail you, Tim. I think you were giving us a culminating statement about our legendary, legends have come and gone ahead of us.
And that idea hasn't changed. I think it's just something that, but you sound truly blessed. The people that have influenced your work, your research, your career are still with us, right? That's amazing. And
it really is a blessing for sure.
Now I should ask actually if Drew has a lab update. Sir, do you have one for us?
Yes. Just trying to
Drew has been patiently waiting for hours for a lab update. So
that's okay. Just been listening to all this physics stuff. I wish somebody would explain to me how I'm going to use any of it. But
it's been a heavy theory meeting, admittedly.
Yeah, they all tend to be that though lately, like for the last 6 months.
How many dimensions are we up to now?
Yeah.
Well,
I can tell you in terms of hands-on stuff. I mean, I can provide you with updates, but people have been pretty. I don't know what you would call it. They've been pretty like heads down, nose to the grindstone, right? So it's been difficult getting the hands-on folks to do a lot of updates. I mean, Mark Sokol over at Falcon Space, he was repairing his laser. He is working on pentacene production for dynamic nuclear polarization testing. I guess pentacene is like the gold standard for materials to test with, right? So they have been perfecting that. Then Isaiah Ritchie with the Searle effect generator, he has a group of folks that are working on that, and he is continuing to make progress there. Last time I talked to him, he was trying to work on like a multi-ring SEG, you know. And then we have lots and lots of smaller projects. Dr. John Brandenburg had one. It was, I believe it was a type of solenoid, and he kind of came up with an initial test there. I'm not sure if he has any updates. And then Robert Francis Jr. And he actually was going to present. He was going to present last month, and then this month he is doing magnet drop tests. He's doing it outdoors, and he is fighting with the weather. So that is kind of hurt both of those.
Okay. Tim, can I present a
Oh yeah. If you do just do your share screen and I will put it up for you, sir.
Okay.
And again, thank you for your patience, Drew.
No, man, just, love to hear theory. Couldn't live without it. Trying to find, this is the thing I just did. Unfortunately, I can't show pictures of any of the hardware, but I can show the results, and the results have been pretty staggering lately. Let's see. Every one of these programs has a different thing. Maybe it's this one. But if anybody wants to see the hardware, all you got to do is come to sunny Florida. So it's.
Drew, are you still using that asymmetric field?
There we go.
Asymmetric fuel.
Field.
Oh yeah.
Okay, good.
Yeah, the more asymmetric the field, obviously, the higher the thrust.
Yes. Good.
So I'm going to zoom in down here because this is where the actual interesting stuff is. This is 4 thruster plates put together, and basically they're just right on top of each other. And this happens to be at high vacuum. So the vacuum is going to be whatever the green line is. So it's green line right here in the middle, which is somewhere around 4 times 10 to the minus 6 torr. So it's in high vacuum. And the power stays on, but because I have a little, when you use commercial electronics in a high vacuum, you can't just put any heat, so everything overheats and a lot of stuff just stops recording. But so the voltage stayed constant. The voltage was at around 5,000 volts. So even though it shows nothing here, this is actually still on. And what I did was I turned it on, and it started making thrust in the negative direction, which is what it's supposed to do. And then at about 1,000 seconds, I turned it off. And at that point, because there is a tiny, tiny bit of heat, or there's a tiny, tiny bit of current being consumed in the system, I think it's heating up the plates. Because the plates go from one drift period to the other. So anyhow, after 1,000 seconds, the plates are as hot as they're going to get. And when you turn off the system, it begins to immediately go to the thermal drift rate of the system. And if you left it off without making any propulsion, it would just continue to drift up indefinitely forever. Because that's what my system does. But in this case, I went ahead and turned it back on. And as soon as I turn it on, it starts making more thrust. And these are thousands of seconds ticking by. So I had about 11,000 seconds of continuous run on the system. And then if I had, at that point, I just shut off the system because, like I said, when things start to drop out, you lose control of the hardware. You spend enough money, you can overcome that, but I don't have that much money to spend on this. So basically, I just shut the test off, and then I started the test right back up and got the next slope. And the slope that it came in at was identical to the slope it had before. So in order to figure out how much thrust the system made in these 11,000 seconds, it's the delta between where it is on the graph, and it's at down here, whatever that is, minus 2.2 millinewtons. These are millinewtons, by the way. And where it would be if you didn't turn it on at all, which is up here around 6 millinewtons. So the difference is 8,900 micronewtons, or 8.9 millinewtons. So in 11,000 seconds of continuous operation, it made 9 millinewtons of thrust. I ran this thing for a total of around 70 or 80,000 seconds, and it produced something like 52 millinewtons total overall, which exceeds the 52 millinewtons is roughly 5.2 grams. The whole system only weighed 4 grams, so it was over its because these are 1 gram sets. So the system actually produced 1 1/4 of its own weight. So had it been set up to free float, it would have lifted off of its haunches. So that's kind of cool. And like I said, so I ran this thing in vacuum, and then I ran the same test with, the only difference was I vented the chamber, so it was running in atmospheric pressure. And it produced slightly less thrust, about 85% as much, but it did produce thrust in atmospheric. And then I took it from here and put it over on the scale, the digital scale, and it did the same thing. Given enough time, it made thrust in the up direction. So that's kind of cool. I got video of that. I'll share that at another time. So, but basically, it's video of watching the scale get lighter and lighter and lighter over the course of, however much time it takes to do that. So I'm 3/5 of my Feynman do stuff. He said if you can't come up with 5 ways to prove something, then it doesn't really exist. So we have 3 of the 5 proofs of making thrust. We've got vacuum, we've got vacuum horizontal, and we've got vacuum, or we've got atmospheric horizontal, we've got atmospheric on a digital scale, which is a completely different setup. It's vertical on a scale. So that's what we're doing here in sunny Florida. We're, basically ignoring the physicist and making the magic happen.
No, Drew, it's amazing, man. It's amazing. You're doing it every day. You're doing it. You're one of the nose to the grindstone people.
Yeah.
Yeah.
So, Curtis, if you want to get together after the first of the year and you've had a chance to sleep, which I doubt you've done in the last 3 months, we can get together and I can show you the data behind all this, the fields, the areas, the what it takes to generate these forces. And
yeah.
Let me. If your stuff falls out of the whatever, you can see if Charlie's physics falls out of your physics or whatever.
Yeah, no, I would love to come down. I would love to come back. I would love to do more film footage and capture whatever. As a preface, and again, because we're live streaming, you have a lot of proprietary stuff, right?
Like none of that would go out on video.
Yeah, a lot of that
wants to link in and behind the scenes do some math, or there's a couple other guys in y'all's little cabal that want to take a look at the
my goal
is I don't mind doing that. That's kind of cool because I can see if maybe you've got some physics. I've got the equation. I can go from field strength and surface area and compute how much force I'm going to make with Charlie's equations. So I don't know how much more equations I need, but his equations, his stuff was real high end, and he had to tune all of his equations to the real world. And once we tuned his equations to the real world, they were spot on. But,
Okay.
you know, there was lots and lots and lots of physics that he didn't see coming that came out of the real world testing. So I don't know how y'all are going to tune all of this physics that requires extra dimensions and unicorn dust. I don't know how you're going to tune that to the real world.
Well, I think my takeaway from that is real world experiments are incredibly messy, right? And that's something. I mean, I know Curtis has had to deal with that ad nauseum. So, you know, they're messy. You get, especially with ions, you get ions, voltage leaks, everything is everywhere. You know.
Yeah, I think I agree with you, Drew, about this, because that's one of the things that I always wonder is when people are adding dimensions or whatever, it's like, what's the motivation, right? Is there a physical, logical reason behind it? So unless there is, I just, you know, just because, like, okay, well, you can add some dimensions and all of a sudden you might be able to add other effects and things like that, but that by itself is not a reason. So I'm with you on that, Drew.
I just, you know, I would love to see a better representation of my what I know I can do than the math that Charlie whizzed out. But his stuff works. You know, it's a simple equation. You plug in surface areas, you plug in fields, and out comes force, actual force. And we're within, I don't know, 20-30% of the forces, because we have to do a little guessing. I really don't know what the fields are, because we're so far above what should be the materials should be able to handle. I mean, you know, we're an order of magnitude above where the plastics and the ceramics should be failing at. So there's just no telling, you know, exactly what we're supposed to be doing, or exactly how we're should be seeing what we're seeing. And I wish I could show you the setup for the scale, but all the pictures I got have thrusters on them. So anyhow, that's it. That's all I got.
Well, Drew, thank you, man. So yeah, if you guys want to do open discussion for a bit, that is totally cool. Again, thank you for the lab updates, and you know, Nathan, thank you so much for presenting today. Joel, thank you for the wonderful insights and questions today. So I mean, you know, I'm overjoyed. December is always kind of quiet, right? Because everybody else has so much going on that I'm really excited that we were able to pull this together.
So, where's Jerry? Did he survive? Did he make it back to wherever he lives now?
Yes. Well, Jared picked up equipment and he is transporting his equipment and he is driving, I guess. So last I heard, he was someplace deep in the heart of Texas, but I might be mistaken. So yeah, he's on the road. He disappeared though. Nobody heard from him for a while. And they were like, is he okay? He's like, yeah, I'm just driving, you know. He had asked me if I wanted to help him drive. And at first I was all for it. And then he's like, yeah, it's like, I'm leaving tomorrow. I'm like, wait a minute, it's a week before Christmas. It's like, I would love to help, but your timing sucks, you know?
Yeah, I mean, he was telling me he went all the way from Canada back to Mark's place, which I guess Mark lives somewhere near Canada. But then from whatever, I guess northern New Jersey, that's where Mark lives, all the way over to the West Coast.
Yeah, he is busy.
Somewhere in there's the Rocky Mountains, so I don't know what he's gonna. I guess you got to go north or south. I really don't know.
Although, you know, if Portland is anything like my area, I mean, he's only like 200 miles south of me. So if they're getting our weather, he's not missing anything. You know, I mean, it's like flood watch to flood watch to flood watch. So, you know, he's probably enjoying the heck out of himself. It's like sunshine, fresh air, birds singing. The rest of us here are drowning, but he's fine.
We had 80 degrees and sunshine today, and now it's freezing out there. It's gone into the 60s. So it's you know, we're expecting the atmosphere to freeze out tonight.
Yeah. Yeah, I don't know. It's just one of those years. Well, they have La Nina and El Nino and La Nina, right? I think La Nina is the warm, wet winters. I think that's what we're having. So, but I could be mistaken.
Was Danny? I thought I saw Dan earlier. Guess he dropped out.
Yeah, he was here. I think he had to go, but you know, but then it's 7:30 his time too. So, yeah, and Joel is Joel. It's like tomorrow your time.
It's already in tomorrow.
Yeah. Well, guys, should we wrap things up for this evening? Seems like it's pretty quiet. I think we've had one heck of a session. Okay.
Yeah.
Well, let's do that then. So I'll say closing remarks. Again, this has been APEC. It is December 20th, 2025. This is the last APEC of the first 5 years. So, you know, and I would say stay tuned. We have another one coming up in January, and I have folks like already who want to speak at that one, and you know, tons and tons of amazing stuff. There's so much movement happening right now. It's amazing. It's amazing.